А теперь можно флешку вынуть, он уже сюда записан, нет? Ну пусть стоит, ладно. Просто чтобы не забыть потом.
Я могу сделать так, чтобы...
Не важно вообще.
Ну хорошо. Да, ну короче говоря, здесь вот когда будет кофе-брейк или еще что-то, то просто остановить трансляцию, это будет пауза. На ютубе это будет просто пауза. Потом, когда продолжите, нажмите это.
А как сюда зайти?
Это вот он, это ОБС у него такой вот логотип.
Ну ладно.
Да. Ну и тогда вот так вот в этой программе, короче, надо открывать. Остальные они не совсем.
Хорошо, что это за программа? ВПС.
Ну это какой-то аналог офиса. Чтобы сделать режим, здесь вот нужно... Не, ну если что, я подойду, но да, это вот просто сделать полноэкранный режим, это вот так. Здесь вот есть панель, которую вот так вот надо сделать, чтобы она вышла. И здесь типа можно вперед, назад, увеличить, рисовать. Ну ладно.
Хорошо.
Так вперед можно просто нажимать.
Вперед это просто нажимать. Вот здесь любое действие просто так, оно просто вперед.
Назад не вот так.
Да. Вот так вот.
Ну да, так теперь двигает объясню.
Ну все. Чтобы не перекрывалось. Мелочь. Все.
Так работает, да?
Да.
Здорово.
Да, он может уйти, и если он идет, то нужно вот так вот зажать, что выкладатель был, да?
Да.
И вот вызвать его вот так вот, тулбар.
Шорткат тулбар.
Да. Сейчас он не очень удобно что-то будет оставаться. Вот он вот так вот выйдет.
Если вот это вот уходит. Ну понятно.
Да.
Слушай, ты мне не прислал, как идти в станцию?
Я пришлю.
И второй вопрос. Я, к сожалению, не смогу остаться на тот доклад, если повтор не будет. Я просто уже доклад.
Не думай, давай на нашем зале.
Ну, так сказать, мы в понедельник увидимся.
Да, я в поле увидимся, да.
Ты меня извини.
Я ничего страшного.
Слушай, скажи, пожалуйста, вообще эти доклады где-нибудь выложены?
Саша,
ну да, то есть, которые вышки, они уже есть, а Сколково надо вводить. В общем, я вышли информацию, да.
Хорошо, спасибо.
Ты
насколько я занимаюсь, я заглядывал, ну, то есть книжки, так сказать, и, в общем, как бы тоже вот самые колфункции, там вот это вот вся наука, так сказать, да, там вокруг Миронова, Морозова. Ты вообще чей ученик-то?
Ну, у меня аспирантура был Шадрина всегда.
А, у Шадрина, конечно. Недавно приезжал в учился на техническую.
Он, да.
А ты, так сказать, к нему не ездишь, да? Сейчас вообще ездить сложно с тобой.
Не, ну почему, есть можно, но я больше работаю с итальянским автором, потому что я в основном итальяниш.
С кем?
Ну, у меня по Беларуси есть Падове. Я езжу, за границей обычно Падове.
Ну вот, а другой вариант еще, так сказать, вы честный, я там жил в соседнем доме.
Надо начинать, да, Саша?
Сейчас, да, будем начинать.
Да, вот уже. Да.
I am the chairman of the morning session, and the first speaker is meeting the equilibrium, reflection equation, algebra, and related combinatorics.
Okay. In order to motivate my title and present a small introduction, I would like to mention first the partition function Z, classical partition function, something like that. Here a matrix, here minus sum k over k maybe, and here we have trace of matrix M in power k, something like that. After the problem is how to construct the corresponding model by using this partition function, how to get Virasoro constraint, and so on and so on. So a lot of problems. But since long ago, I am working with another algebra which can be put here, the generating matrix. I will explain what I mean by generating matrix. Here, generating matrix of this algebra, and how to modify the corresponding measure. This algebra is called reflection equation algebra. And finally, in some form, this reflection equation algebra is called modified reflection equation algebra. I will explain. But finally, the main purpose of my study is just to construct a generalization of that. You know that if we want to compute with the integral, it's necessary to present this measure in another way. So it is sum here a van der Waals determinant squared. And if we pass to Q situation is just related to reflection equation algebra. What is another of that? You know, maybe you have seen the paper by Zabzin and company. Finally, here sometimes one put Q, here Q minus 1, or something like that. So, and here, without change, without modification, it is just this expression. But maybe it's necessary to change here as well. And so I propose to consider reflection equation algebra, because by using this algebra, it's possible to understand what is another process. So it is my aim. Another possible application, you know, the notion weight system. Weight system. It is some invariant by Vasilyev, but the weight system, I don't know, it's was introduced by Kontsevich, and with construction uses some Lie algebra. Mainly it is just algebra GLN or superanother of that. Thus here the author of this paper related to this problem. But I will not speak about that because it is not yet done. It is now in progress. but I will speak only about this algebra, which allows us to generalize all this construction. So I will speak about possible generalization of this type. Okay.
Dim, could you say a few words about what do you expect from this partition function? What property you need?
It is question to your student. Finally, you are right. It's necessary to understand first what property we would like to have. For example, consider Kontsevich construction. In Kontsevich construction, we have the algebra, envelope in algebra, we calculate something, and as a result, output we have a function or a number, a function of commutative generators. And finally, I would like to say that it's possible to do in frames of my construction. But here the problem is that here in construction by Kontsevich, Kazaryan, Landau, and so on, and students, we have some relation which is called four terms relations. And what is analog of four terms relation here, I don't know for the moment. We put this question to some student, but it is not yet done. So, I repeat, I will speak about a good algebra which comes to our possible with construction, and now I will explain some properties of this algebra. So, we are dealing with braiding. What is braiding? Braiding is operator, invertible operator acting in the space V squared in the same space, such that in V in power 3 we have this relation. This relation is called braid relation. It is not Yang-Baxter equation, but it's possible to change something and to get from this relation Yang-Baxter equation. So Y is identity operator, and here I present two simple examples, simplest. So I is equal to the usual flipper, so the flipper as follows, and PMN, it is thus super analog of super flip. It is more or less similar, but necessary to take in consideration the parity of it. Okay, so now,
Нет, назад, к сожалению, не работает, работает только через эту штуку, которая была здесь. Что исчезнет? Вот это то, что было здесь, как эти не работают?
как?
Нет, стрелочка другое.
Ну, может быть.
Это выйти совсем из этой самой системы.
Это назад идет, да?
Да. Еще.
Стрелочки?
Нет, это в конце, надо самое начало.
Это идет
это все конец. Намного раньше.
Не сместить.
Может быть, вот тут вот, нет?
Нет, это не работает. Была вот такая штука сложная, как ее сделать?
Еще можно нажать и подержать палец на экране.
Там же эти аутентики, кстати, эти штуки. А какой долг еще?
Это рефреш, скорее всего. Тут, ты помнишь, был это вот это? Может, кстати. Как появилось, что может быть?
Что тут было?
Вот.
Окей. Okay. So, you see my previous example have this property, some type of transposition of braiding is called involutive symmetry. So, if we have this relation, it's called involutive symmetry. But the more interesting and more general, it is braiding satisfying this relation. the corresponding braiding is called Hecke symmetries. And if we consider the corresponding operator k may be comma k plus 1, because the operator acting in v squared. We have such presentation of Hecke algebras. So you see, such k is nothing but a representation of Hecke algebras, or Hecke-Ivachori algebras, because it's just case which is called Hecke algebra corresponding to from A series. Ivachori, it is just A series. But we consider Hecke algebras generated by identity unit and with generator, and finally we have a representation which associates to tau are put in the good position. And finally, this representation is called R matrix representation. Here I present two examples. You see, these examples come from quantum group. This example is maybe the most known for the dimension 2. It is more or less similar, but here minus and here minus. So if Q is equal to 1, we have here the usual flip, matrix of the usual flip. I fix basis in V. In the V squared, we have the corresponding basis.
Можно нажать на экран и подождать.
Sure. Okay. Okay. So I see my mistake. My mistake is I touch with screen. It is not to do. Okay, so we have here two examples. We have here a deformation of super flip, and here deformation of the usual flip, but with modification of R, we multiply by P, we have just an operator which is called quantum R matrix, which satisfies quantum Yang-Baxter equation. Okay, so now, example, if we take R the usual flip, with deformation of the usual flip, for example, deformation of Greenfield type, we have the following. What is P minus? P minus is here. Okay, so P minus here. So we have analog of symmetric algebra, analog of skew symmetric algebra. We have here just in the bracket difference, and here sum, and product of this expression and this one, it is equal to 0. It is just a Hecke relation, and you see, so we have R analog of symmetric and R analog of skew symmetric algebra. And I introduced many years ago the so-called Poincaré-Hilbert series. It is a very natural notion, dimension of K homogeneous component, and here similar. And for Q equal 1, we have similar construction, but for R involutive. Now, examples, P minus is equal with polynomial in the usual for the usual flip. We have P minus as follows for the super flip, and I constructed many years ago in the late 80s example. I call them exotic examples. So it is just as follows: P minus is equal the polynomial of degree 2, but here n may be any million, for example. And if we have here a polynomial, we call corresponding R even. So it is just corresponds to the K when we are dealing with boson, no fermion here. if P minus is a polynomial. But if we know P minus, we can compute P plus, because many years ago I shown this formula. So this formula is classical. If we have the usual symmetric and skew-symmetric algebras, but in my situation, this relation is called as well. Okay, and so this result belongs to Vietnamese mathematician Hun Hon Hai. So P minus and consequently P plus is a rational function. So we have here polynomial of degree R, here polynomial of degree S, and finally the couple R-S is very important for all calculation. I call this couple R-S by rank. And you see, by rank is an element of superdimension Mn. In this sense, I would say that my construction is a generalization of super situation. So everything is super situation in some sense, because instead of Mn, we have Rs. Okay, and now if we want to calculate dimension of space, it depends what dimension. There is dimension usual and there is a dimension super, in super situation. In quantum situation related to a quantum dimension. And you see, if for example we have a super space, even part, odd part, and what is dimension in the usual sense? It is plus, M plus M. But quantum dimension and super dimension in this situation is minus, M minus 1. So in general situation, if you have a space V and R, Braden or Hickey type, it's a question, what type of dimension do you want to compute? Okay, now I pass to other algebras which are related to Braden, Braden or Hickey type, Braden's Hickey symmetries. So I presented here two algebras. One algebra asymmetric, the other is askew-symmetric, and now this algebra. What I mean by this relation? A is a matrix. Entries of this matrix Ly(j). Okay, but now what is L1? L1 is the product, product with identity matrix. So we have here matrix n squared by n squared, and similar situation here. And this relation is good because all matrices here are on the same dimensions. We calculate all that. We have some relation between entries. And finally, the question is how is dimension of this algebra? It is a right statement or not, that if R is a deformation of the usual flip, in this algebra we have a homogeneous component R deformation of the usual component corresponding to the usual flip. It is so. So deformation in mathematics is called deformation of such type, flat deformation. But you see, I consider simultaneously with algebra, L hat. And what is difference? Here 0, here we have some linear term, because on the left hand side we have quadratic term, and here we have quadratic equal to something. Here we have linear term. This algebra is denoted L of R, and here L hat of R. It's called modified reflection equation algebra. Okay. Now, you see that if R tends to the usual flip, as Q goes to 1, we have for the modified reflection equation algebra limit enveloping algebra, and for non-modified symmetric algebra of GLL. But in spite of this fact that for Q which is not to inner. We have a modified reflection equation algebra, which is isomorph to non-modified reflection equation algebra, but for Q equal 1, it is not so, because here we have enveloping algebra, and here we have symmetric algebra of the set. Okay, so it is a strange situation. It is not so strange, but if we forget about the Q equal 1, we have isomorphism. For Q equal 1, isomorphism fails. Okay, now, if instead of R I put here the usual flipper, we have with relation quadratic relation and with relation quadratic linear relation. I said it is a good writing of usual commutative algebra. It is just a relation in symmetric algebra of GLN, nothing more. For example, if n equals 2, we consider the matrix A, B, C, D, 4 terms here for 4 entries. And if you write down with relation, what is L1? L1 is AA, BB, CC, DD. 0, 0, elsewhere. So if you put with matrix and with relation, and P in this situation is the matrix of the usual flipper, you calculate with the relation and you obtain relations AB is equal BA, AC is equal CA, and so on. So you have 6 relations. Many relations, 16, but all relations are not independent. So only 6 relations here are important. And if you compute with a relation here, you have the following system: AB minus BA is equal B, AC minus CA is equal minus C, and so on. So it is just the system which is the defining system for the enveloping algebra. Okay, now I want now to state the main, if you want, the main statement in this part. For our algebra, it means that we consider the modified reflection equation algebra, which is deformation of that or not, and non-modified. And here I want to introduce for the matrix L, A, B, C, D. I want to introduce the generalization of the trace. So the my trace, analog of the trace, is just the usual trace, but here we put the matrix C. What is the matrix C? The matrix C is completely defined by the initial R, by initial Hecke symmetry. So now, instead of the usual trace, we are dealing with new trace. And this trace is well defined for big part of the whole set of Hecke symmetries. With matrix C is well defined for the braiding, which are called skew invertible. I don't want to explain what doesn't mean skew invertible. This term was proposed by Lech Agiyevetsky, but finally, for almost all R, C can be found. And now, by using new trace, I introduce in this algebra non-modified and modified reflection equation algebra corresponding to R, to Hecke symmetry. I introduce the following expressions. With expressions, trace, new trace, our trace, for L. So I introduce this expression, which is analog of the power sums. You see, power sums expressed with a matrix. Trace, if trace is usual, it is just power sums with respect to eigenvalues of the matrix A. And in our actual setting, it is just analog which is living in reflection equation algebra, or say the same in modified reflection equation algebra. And you see that if you do the same for the so-called RTT algebra, the well-known quantum algebra, quantum matrix algebra, which is just as follows. And you know that this matrix is normally used in the construction of Leningrad Mathematical School, or by Drinfeld, and so on and so on. But I would like to say that this algebra, which is an example of quantum matrix algebra, and my algebra, reflection equation algebra, is also an example of quantum matrix algebra. And they are other quantum matrix algebra. But this property, with construction, can be defined in this algebra, but good property are only possible in the frame of reflection equation algebra. Okay. So now I introduced this expression. This expression are analog of power sums in this algebra and modified reflection equation algebra. Now I want to introduce the following notation. L1 overlined is L1 without modifying with that. L2 overlined is L1, and here instead of P I put here R. You know that in the usual motivators, in the usual calculation, for example, in this algebra, what is T2? T2 is just T1, and here we put 2 flips. That's all. 2 flips. So flips as you wish, 1, 2. But it is evident. So what is T3? It is T2, but transfer it on the third position, next position, with flip here 2, 3, 2, 3, and so on and so on. But here, instead of the flip in this construction, we use R. So L2 overlined, L3 overlined, it is more or less similar construction, but instead of P, we use R. And this notation means that I consider product of L and of L overlined, number overlined. For example, if I consider the matrix L of dimension 2, 2, we have L1 as follows. I presented it above, and here L2 overlined is just the same matrix, but here R and here I minus 1, and so on and so on. Okay, now the main claim here, if we consider a matrix representation of any element belonging to Hecke algebras, any element with representation, I said it, is called a matrix representation. After that, I put here the product of the matrix on the previous page as follows, and after that, I take a good trace, a trace. And finally, we put here what we get here, what we get here. We get here element of our reflection equation algebra. I deal now with reflection equation algebra. The statement by Isaev Pyatov, this element is central. So it is an explicit way to get central element of reflection equation algebra. I don't speak now about modified reflection equation algebra, but it is not a big deal to show this statement. It is more or less easier, but it is very important. Very important. And finally, here I recall you what is a matrix representation, and with map sending the reflection equation, Hecke algebra to reflection equation algebra is called characteristic. Okay, but now what is power sums in our settings, I presented with. It is similar to the classical construction, but instead of usual trace, I use our trace. Okay, but it's possible also to define an allele of Schur polynomials. Schur polynomials is constructed by the same scheme on the previous page by Ferry and Pyatov. But here, what is Z? It's necessary to take correctly Z with this problem. And that here, it is some idempotent living in Hecke algebra. I don't want to explain how it's necessary to get a construction of this idempotence, but it's possible to do. And if you are interested in this construction, so you can consider the paper Ogievetsky Pyatov, which is called Pyatov lecture on Hecke algebra. I don't know exactly it exists on the archive, or maybe not, but it exists. It's possible to get. Okay, so now, what is classical Frobenius formula? Why do I speak about Frobenius formula? A little bit later, I will speak about Frobenius Capelli formula. So, because I want to show you that on the reflection equation algebra, it's possible to develop many aspects of combinatorics. So, it is just my aim. So, classical Frobenius formula. If you have here a basis given by Schur function, classical Schur function, but expressed via matrix, and here you have a basis expressed by power sums, if we put here nu, it is the usual definition. Here pk, I defined it, but here the product of them. So passage from one basis to the other one is just with coefficient, which is nothing, character of symmetric group. So here we have lambda, it is just symmetric group representation labeled by lambda, but nu, it is just it is evaluated on element whose cyclic type is nu. And in our situation, the formula, Frobenius formula, is thus similar. Here we have our power sums, here we have our Schur functions, but here, instead of character of the symmetric group, we have character of Hecke algebra. And finally, this result was more or less known since long ago. It was obtained by Arum Ram, but for situation related to only quantum group by Greenfield, so only one is possible in his article. But in our proof, any R is allowed. So now I would like to say that the generating matrix, I call matrix L, generating matrix of the algebra reflection equation or modified reflection equation meets Cayley-Hamilton identity. You see here the usual, more or less usual relation, but Q here and E1, E2, and so on are particular case of Schur functions which are called elementary symmetric functions. Elementary symmetric functions are constructed by the same method as above, but of course E, Y, Y, lambda mentioned above, it is just correspond to the elementary symmetric function that is corresponds to the diagram diagram one column and diagram corresponding to one row is called full symmetric function. It's very natural. So you see, it looks like the classical one, but of course here sure functions are constructed by our method. And this relation is valid if R is even. So we don't consider here the fermions, only bosonic case. And I recall that coefficients here are central, as a particular case of short functions. And finally, it doesn't matter. I put here on the right-hand side, on left-hand side, it changes nothing. And if I apply here a good trace, our trace, so we put here the relation which is analog of Newton relations, and so on and so on. So many aspects of the usual combinatorics can be generalized to this case. And if you go to internet, you find many possible ways to generalize the construction of the usual symmetric functions. And I state, it is my feeling, as you wish, that our reflection equation algebra and modified reflection algebra is just the background to generalize the usual combinatorics. Okay, so now we introduce new mu y, roots of the previous equation is as follows. So instead of L, I put X, for example. I have an equation. It's possible to introduce the notion of roots of this equation. And so it is just for introducing the roots. The sum is just first coefficient, with sum is the second coefficient, and so on and so on. So as you wish, mu y are roots, or they are called eigenvalues of the matrix M. It's very natural. Okay, and now I consider the bigger algebra, which is reflection equation algebra, but completed with mu1 and so on. And of course, mu1 and so on are supposed to be central, to commute with other generators. Okay. Now, if R is not even, its by rank, I suppose, is Fm. We have mu y, but above, besides we have nu I. So mu I are called even eigenvalues, and mu I are called odd eigenvalues. And now, if we want to express power sums by using mu and nu, we have this formula. This formula was published in paper by myself and Pavel Sapon and Pavel Fiatov in 208, maybe I've forgotten. But finally, we have here analog of polynomials of symmetric functions, which are analog of Hall-Littlewood. And finally, in order to pass from our writing to Hall-Littlewood polynomials, it's necessary to put t is equal to k in power minus 2. Okay, so you see why I presented here this formula, because if you have, for example, this writing, it's necessary to give, make some sense to this expression. So it's necessary to express this trace by using mu1. And so formula presented above is just another of that. But of course, it is not sum as follows. This formula is good for classical case. But in our case, we have here some coefficient dy depending on u, presented on the previous page. And moreover, for this situation, it's possible to consider super case. And super case is given by a similar formula, but containing uy and mu1. So you see, it is just the general situation. Okay.
Di, is it polynomial?
What?
Di,
What is polynomial?
Di is expressed in terms of polynomial. The denominator cancelled.
It is polynomial. No, dy is not polynomial, but if you put dy and multiply by mu in power k and sum, it is polynomial. Okay, so you see what we have a set in our setting, of course. Set of power sums and set of Schur functions. Particular case elementary, full symmetry function, and so on and so on. So the question, what are relations between Schur functions? Relations between Schur functions are given by classical Littlewood-Richardson, so coefficients are classical. But they are symmetric functions with respect to mu y multiplied by q in minus 1. In general situation, when situation is not even, it's necessary to take also q in power 1 multiplied by mu 1. That's on its own. But now the relation between two families, Schur functions and power sums is not classical, because now instead of the usual polynomial, which are power sums expressed by mu, we have whole Littlewood polynomials. Okay, so here I present a way I want to say the following. Finally, what is main difference between our construction and the classical construction? If you are dealing with, say, enveloping algebra of GLM, and you want to, you have a relation, one element, another element, minus inverse equals something linear here, some relation in the enveloping algebra. So, what is presentation of this algebra? How it's necessary to do? We take this element, we take element belonging to the space V, and we apply. And what is the way of applying this? It is just, we present this element by using the so-called Bosinization. It is element from the space V and the space V dual. And we apply this element to this is the usual way. It is nothing but pairing. And you get xy and here delta, y delta. Because pairing of this element with this element, I forgotten to say that I take here the dual space, dual basis. Pardon. Dual basis means that if I apply pairing in this way, I get the usual delta. But if I apply in another sense, it is not delta. It is just some matrix. And what is it, this matrix? It is matrix more or less inverse to the matrix C above. So we are dealing now in braided case. And braided case different from the classical case is the following. We have a big category generated by V and V star, VQ. So V in any power, V star in any power, and so on and so on and so on. So big category. And now, if we want to apply pairing in this way, we have one answer. If we use another ordering, we have other answer. Because in our braided category, the pairing depends on the order. Okay. Now, I would like to say a couple of words about Capelli formula. What is Capelli formula in the classical case? In the classical case, it is as follows. We take the matrix L, the usual matrix with commutative entries, and what is matrix D? D is composed from partial derivatives. So partial derivative as follows. You see, I use here the following partial derivative. It's necessary to apply pairing J and K and Y and N. Normally, in this formula, one put here transposed. By with my definition, it is just as follows. But in principle, it is not so important. The important thing is the following one. We consider now the following matrix, L hat, and this matrix with entries L, Y, J hat is as follows. Here we have summation. And finally, the statement in classical situation is L hat is generating matrix on the enveloping algebra GL. In our situation, it looks similar, but a little bit different. So classical Capelli identity is determinant of this matrix, all here entries of this matrix, here entries commute with each other. Times determinant of this matrix, here they commute between them as well. And on the left-hand side, it is not so easy because this matrix, entries of this matrix do not commute with each other. And finally, it's necessary to present here determinant with a curve, carefully. Finally, determinant with here is called row determinant, and here it's necessary to apply shift. Okay, so passing to the Q case, now we have the following situation. Let A be the generating matrix of reflection equation, and we discovered what are partial derivative in L, Y, J. So D is matrix composed from partial derivatives. I don't explain here what are partial derivatives. It's necessary to take more time. And finally, I don't want to do that. But if we compose the product as similar to the previous page, we have L hat generating matrix of modified reflection equation algebra. It is very surprising situation. Because if you take L generating matrix of the usual reflection equation and D composed from this derivative in quotient marks, you have matrix, and what equation of this matrix is good. Finally, the relation on this matrix is modified reflection equation relation. Okay, and the corresponding Capelli identity is as follows. Here determinant corresponding to R, here determinant corresponding to inverse matrix, here Q in power, and on the left-hand side it's necessary to present in this way. If you consider the paper by Yakunkov, which is called, it is immanent. So they generalized this formula to other immanent, not only determinant. not only determinant, but in classical situation. What is Q analog of immanent by Kunikova? It's what recently obtained by Zaitsev, student of Pavel Sapkov. Okay, now I want to discuss the last subject of my communication. I want to speak about one result by Perelomov-Popov. What is result by Perelomov-Popov? We take the power sums, because k may be 1, 2, and so on. And we consider the corresponding Casimir operator. Casimir operator, it is just image of z, if instead of z we consider L is product, it's necessary to put here, we consider the product of the matrix L and the product and matrix composed from derivatives, and finally we consider all this stuff as vector fields. I call this vector fields Euler vector fields. And we have a corresponding Casimir operator. But now we consider the finite representation of our algebra. And if we consider representation which is labeled by partition lambda partitions, then the corresponding Casimir operator has a scalar image. It is a very known theorem. So we have identity operator and here a number. Okay, now, what is image of this Casimir operator? What is just result by Perelomov-Popov? Result by Perelomov-Popov says that we have image of Casimir character. On the previous page, I forgot to say that chi is just called character. Here we have Casimir presented by this formula, mu hat here, but mu y hat here is as follows. So I presented this result by Perelomov-Popov in this way because I want to generalize to say the following. A reflection equation algebra is possible also consider finite representations, consider analog of Casimir operator. Is a question, what is the value of mu in mu setting? So this formula is given. It is some pages above. But what is the character of mu? As you wish, I call this character of eigenvalues. And I recall you Cayley-Hamilton identity. Now Cayley-Hamilton identity for L hat, which is generated matrix for modified reflection equation matrix. So I consider the eigenvalues of this equation. I introduce the eigenvalues in my algebra, so I consider central extension of my algebra because all coefficients here are central. So I do very naturally here. And finally, I introduce a character of mu, of roots, or eigenvalues, as follows. And the Perelomov-Popov formula can be expressed as follows. Character of Casimir is given by the following formula presented above. But now I apply here character to any mu hat. So it is just formula by Perelomov-Popov. And now the question, if we consider analog of formula expressing via roots or eigenvalues in our Q situation, what is character of the corresponding eigenvalues mu? And result is follows. Casimir, it is just presented by power sums as follows. This formula was presented above. And now, recently, Misha Zaitsev, student by Saponov, proven this formula was conjectured in paper not, this paper is not published, but finally this formula was known before. But demonstration proof was absent, and Zaitsev have proven this formula. So if we consider the character of mu as follows, and put this character here, we have character of Casimir. It is just a result by Zaitsev, but now we free authors prepare a paper devoted to this problem. But now, because it's possible to pass from the non-modified reflection equation to modified reflection equation, it's possible to get very quickly, without no problem, what is a result by Perelomov-Popov, but in Q situation. So now Casimir is power sums L hat, is presented by this formula, and now character of mu y, it's necessary to put here, is presented by this formula. If we put here Q equal to 1, we get just formula by Perelomov-Popov. We have just character presented 2 pages above. And I more or less finished, but I would like to say the following. You know that in the theory, Gurevitz, in some sense Kontsevich as well, so the so-called cut and joint operator play very important role. Cut and joint operator are more or less Casimir operator, but it's necessary to put here the normal ordering. So difference between Casimir and cut and joint, it is just normal ordering here. And finally, one put here normalization. This factor for me doesn't matter. But what is analog with the formula in Q situation, in the reflection equation algebra? In reflection equation algebra, we know what doesn't mean this expression. R analog or Q analog of trace, we know it. The only question is what is normal ordering here? And normal ordering is proposed recently by myself at Safonov, and finally now it's possible to introduce R or Q analog of cut and joint operator and to consider the problem which is generating tau function from given the simplest tau function. We take simplest tau function, for example, 1, we apply E in power W, and W is just a cut and joint operator. And the question is whether it's possible to get in this way an analog of tau function similar to the classical way. For the moment it is not known, it is not yet done. And finally I explain here this story because I would like to have students which are interested in all this stuff. So I stop here. I would like only to say that it's possible to construct some by Baxterization, construct some generalized Lingian and so on, and to use this generalized Lingian in constructing beta subalgebra and so some integrable system. But it is another story. I'll stop here.
Any questions, remarks? It's just a technical question. You introduced a rank which consists of pair of integers Rs or Mn. So the sum of these entries, is it related to the dimension of the matrix L?
The dimension of matrix L?
Yes.
Yes. For my situation, it is squared matrix, always squared. So you see it.
But is it true that R plus S is equal to the size of this matrix?
So the answer is as follows. If T minus of T, the Poincaré Hilbert is as follows, plus 1. So dimension of the space V, dimension, usual dimension, in the usual sense, dimension of V is just 1. And all matrices we are dealing with are of dimension n times n. That's all. But the question is, if you take matrix of dimension n by n, and you take trace of this matrix is n, nothing more. But in our situation, trace, if you take good trace, a trace, it is not this. You take here trace 2, because it depends on the by rank. By rank R, S. And in our situation, my example here, we have here 0, we have even space. So only 2. Here, that's all. And so all classical dimensions depend on the by rank, on rank.
So in this case, the by rank is 2, 0.
Here by rank is 2, 0, yes. And you see, I give you some example, and I ask you to calculate. But you put the question, what dimension should I calculate, classical or quantum? Quantum is more important in this time.
It's clear.
It is more important. Similar in super case, m minus 1. It is not m plus 1.
But even though the by rank is equal to 0, you have Hecke algebra of size of dimension n.
In principle, I have any dimension, because if you have Hecke algebra which contains n elements, so n minus 1, you can embed it in next algebra, so you can suppose that you have a big n. It doesn't matter finally. If you have R, which acts in the space V squared in the same space, you can take this algebra very big. It doesn't matter. But the characteristic which matters is just rank or by rank. So all calculation finally on the output doesn't depend on the concrete R matrix, on the concrete Hecke symmetry. Doesn't matter. The matter is only by rank. So finally, conclusion. The example by Griffin, and so on, enough to apply our calculation and to get a result. Because here the rank is 2, 0, and if I take my exotic, in quotation marks, examples, the result is the same. All dimensions are the same. But if you are interested in quadratic algebra, so what is quadratic algebra? A set of generators and set of relations. I present you here a big family of quadratic algebra, which were known about before. But result of all numerical calculation are the same. That's all.
Any further questions?
Yes, but I think I didn't get it. So what are the restrictions on the on the matrix R? So should it always satisfy the breaking relation, or can I say take a product of several like matrices and then build this construction of the L operators?
As I understand your question, the problem is why do I take always Hecke symmetry? Because in this situation, if I consider the corresponding reflection equation algebra, deformation is flat. It's good deformation. I take classical situation, I replace the usual friction by R, and we have a deformation which is good. If I take R, which is, for example, Biermann, Wenzel, Murakami, it is not a flat deformation. Biermann's Wenzel Murakami, it is just a matrix braiding coming from B, C, D series. My case considered here is just A series. A series, healthy symmetry. But if I come from here, I have a Biermann, Wenzel, Murakami symmetries. But from these symmetries, if I take the same relation, T1, this relation, or L1, L1 minus and so on, it is not a flat deformation. It is back deformation. You consider classical case, for example, consider the following algebra, two generators, but relations are xy minus yx and xy minus 2yx. Okay, I factorize by that. If q equal 1, we have one relation. Two relations with the same, as the same. And q, which is not equal to 1, the algebra is much smaller. So it is the general situation. And I am interested in situation which when deformation is good. So proof of good deformation, it is not so easy normally. And for series BCD, if I take R as you propose the product of some healthy symmetry, so we have a new braiding, which is braiding does not lead to a good deformation. In principle, it's possible.
So you probably assume that your Q is a kind of generic value.
Generic, yes. I forgot to say that Q is generic. For Q special, it is not good with Q.
But what about the roots of unity?
Roots of unity is forbidden for me.
What happens wrong with roots of unity?
I don't know. I am not interested in Q. I am interested in good deformation, because if you have a good deformation, classical commutative algebra, after that you deform it. So the question, what is corresponding Poisson bracket? It's possible to put this question. But if deformation is not flat, it's not good, so Poisson bracket is absent.
Well, it's not absent, you cannot construct it.
Что ты говоришь?
It's not absent necessarily.
Absent Poisson bracket?
Yeah. Well, you cannot prove it's absent.
Absolutely necessary, it is absent.
It depends on definition what it was.
Of course. I speak about usual Poisson bracket.
Okay, no further questions. We have a break. Thank you. So we have break. So how many time to finish? 15 minutes. 15 minutes.
Сейчас получаю, да, в понедельник я приеду. Я на
Сейчас, а вам не нужно ничего будет писать?
Нет, я если что на доске.
На доске? Не, а вообще вот тут такое дело, что просто ничего не, что на доске пишется, оно ничего не.
Мы с тобой еще увидимся.
Вы сможете на слайд? А мне могут писать?
Там нельзя писать на доске?
Ну, не, можно, но только это будут вот живые те, кто онлайн. То есть как бы вот это единственная веб-камера, которая
Да,
есть.
нет, дело в том, что если потребуется, это не будет типа замечание по слайдам, будет что-то другое.
Что?
Но если я что-то напишу, это будет какой-то пример, и это будет не то, что будет какая-то, чтобы заметить по слайдам или какое-то замечание. Ну ладно, постарался, я понял, я постарался не писать.
Да, ну здесь типа есть сейчас.
Ну доска есть. А потом как эти статус обратно
строить что-то типа Индианы, а Индиана первоотрядца зависящая от Уилла.
Не отмените то, что писал, как на режим меня слайды.
А назад ставишь? Нет, предыдущий слайд где-то стены.
Ну я имею в виду, что если на режиме ручки, тогда нажимаю и он меняет слайд. А сейчас он на режиме писания, да? Так что такое нельзя писать надо. Я понял, ладно, хорошо.
Ну вообще желательно вот это использовать.
Я понял.
Нет, ну даже без параметров ты есть линейный. Вот смотри, я пример люблю приводить. У тебя есть просто линейная скобка СВ. Так сказать, h с x это 2x и так далее, 3 соотношения. Вот у тебя фасонная структура. Потом я говорю, умножьте справа все на h, чтобы получить квадратично. Значит, h с x будет не x, как было раньше, а hx. Значит, оказывается, что эти скобки линейные квадратичные, они промеж себя согласованы. И спрашивается, а как проекстовать просто?
Да. Кнопку надо в середине.
Да, надо вытащить.
В середине.
Я не видел. Это не трогать.
Это твой, наверное.
Это потом. Да, это не мой.
Подожди.
Флешку тоже берите.
Еще вытаскивать, да?
Сейчас она здесь.
Я пойду пока.
Всё.
Спасибо большое.
Там, скорее всего, у меня в download.
Там присели. Лучше не так, как не браузере, а
Да,
флешкой.
браузером, да.
Конечно, просили паузу сделать, но паузу мы боимся.
Ну, мы с тобой увидимся в понедельник в Ярославле. Да, извини меня, так сказать, на похороне.
Это вот приложение, да?
Его рекомендовал.
В понедельник уезжаю. Мне билеты прислали.
Я понял. То есть прямо с Ярославля? Откуда?
Окей.
Я в понедельник из Ярославля должен уезжать в Москву, а во вторник я улетаю.
Вы не дадите просто
The last one, the same as the and yeah, I think we can sit with courier.
Okay, sure. Okay.
Вот это почему не сработало? По-моему, ты когда пытался это сделать, он был в стадии переключения.
Да, если уходит он. Да, уходит.
It's possible, but the problem is, for example, for the metric cell, what is transposition? Because in usual situation, if you are given this graph, you are interested what is transposition of the matrix to something real on the diagonal and so on. It is not it. It is not simple.
No, I thought about
No, but clearly I don't believe it.
No? Okay.
Я понял, что.
Что такое?
Я понял, что посмотрели.
Ну, твой телефон у меня есть? Максим, ну я так понимаю, что какие-то твои студенты, ладно, так сказать, пришли в Пашу, нет? А вот такие кайцы. Вот я его видел. Но он только в мою память запал, так сказать. Может, он заинтересуется. Ну, вообще-то, да, если он хочет, я, в принципе, в следующий вторник приеду, вы же с Пашей общаетесь.
Гипотеза состоит в том, что если нет, там вот такая, там дальше вот такая идет чисто там гипотеза, что если это конечная форма, то тогда все и вот эта гипотеза
на той неделе была в этом месте.
You can just take some money,
Это когда в основном
он не раз мужчина. But there is yeah. But you can use it in the bus, ground.
I will send you some list of corrections that I still wanted to introduce, but never did. Right? So probably the correspondence between the pages is different based on the law approach.
Ну и там это стандарт. Есть. А дальше есть на втором шлагбаум уже в районе Сколково. Там, как бы, честно говоря, это менеджер, ну как там менеджер вроде себя смешно. Но нет уверенности, что система работает правильно. Поэтому лучше это отключать, не созвонить. Я уверен, что это хорошо.
За бесплатный СГБР не предполагаем.
Так, когда же нам начать?
Пока бы начать, надо закончить.
Как бы только в камеру, вторая на аудиторию, поэтому то, что здесь было в тексте написано,
поставить, он вообще не слышал о том.
Не, ну то есть здесь можно настраивать касательно, не знаю. Какие задачи? Достаточно.
Завтра пойдешь?
Нет, к сожалению, да, завтра буду доклада, я сразу после доклада не поеду. Да. Завтра будет проверить оборудование станции. Нет, к сожалению. А, да, который открытый. Сколько это будет? У меня есть 6 месяцев.
The next speaker is Satiris Georgievich Konstantinovizis. And his talk n-simplex maps on groups and rings.
And rings and drinks.
And drinks. Drinks.
And drinks. Yeah, thanks very much. And first of all, I'm very grateful to the organizers for the opportunity to give a talk in this nice conference. So I will be talking about n-simplex equations on groups and rings. So that's my plan of my talk. So the first part will be I'll say a few things about n-simplex equations in general. Then in the second part I will focus on a particular member of this family of equations, the tetrahedron equation, and I will explain how its solutions are related to matrix refactorization problems. And I will show a new approach for constructing such solutions, which is a joint work with Sergei Bonin. Then I will show a method for constructing four-simplex maps, like solutions to the set-theoretical four-simplex equation. And I will present some first classification results, which is with my student Mikhail Chirkov. N-simplex equations are just generalization of the famous Yang-Baxter equations. They have very many applications. The application range in various fields of mathematics and physics. But for my point of view, the most important application is, well, the most interesting to me application is that they are related to integrable systems and discrete integrable systems. So that's the first three, the most famous members of this family of n-simplex equation. This is the Yang-Baxter equation or the two-simplex equation. This is Zamulodzikov's tetrahedron equation, the three-simplex equation. And that is the four-simplex equation or Bazanov-Stroganov equation, but I will explain how they are defined in the next slide, so don't worry about that at the moment. We are interested in the set theoretical solutions of these equations. and formally the study of such theoretical solutions was proposed by Dень in 1990, but the first solutions a little bit earlier appeared in the work of Sklianin. We will call such solutions, such theoretical solutions to the n-simplex equation will be called n-simplex maps, and that's terminology given first by Buchstaber, but everyone is giving reference to the Selov because of Buchstaber wrote it in Russian, and then the translation in English was wrong translation, Yang-Baxter transformation instead of map. So the most interesting property of all these equations is that the local n-1 simplex equations generate solutions for n-simplex equations, and I will explain what is local a little bit later. Here, we focus on methods for constructing 3 and 4 simplex maps. So what is a tetrahedral map? We start by any set, arbitrary set, and we get a tetrahedral map is a map that takes 3 elements of the set and gives functions, 3 new elements in the set, which are functions of the initial values, and it's called a tetrahedral map if it satisfies the tetrahedral equation. So between them is we have just composition, function composition, and these indices mean that what means the indices ijk, 3 indices. Ijk means that all these maps actually are defined on the set of 6 elements of the same set, and ijk means that they act on the I, j, and k of the 6 elements exactly as the map, on the rest trivially. So 1, 4, 5, that means that I take the act at the first, the fourth, and the fifth elements exactly as the map, so they change these elements to functions u, v, and w of these elements. So x1, x4, and x5 is being changed to u, v, and w of x1, x4, and x5, and the rest remain as they are. So the rest of these matrices are defined in a similar way. And the most popular example of such solution to this equation is Cauchy's electric network transformation, which is related to electric networks. So, which are the most some key results? So there are very many results, but
comment on this Cauchy solution. X and Y are from what sense?
Yeah, sorry, I should say, so I said that X is a set, but here I understand that you have some Russell functions. X, in every application, you define what it is. Here it could be the complex field, it could be CP1, it could be, yeah, sorry about that. So the most important results, from the point of view of integrable systems is Sergei's classification list on these tetrahedral maps. Then the relation between tetrahedral and tetragon maps. It's a work by Demakis and Miller-Huijsen. Then the relation between tetrahedral maps and 3D lattice equations. So these maps are related to 3D lattice equations via their symmetries. I can show an example because this equation actually appeared in the talks of Rustem and Ismail. So this equation, which was the H1 equation, or discrete potential Kardashev equation, this times f n plus 1 m minus f n plus 1 is equal to a times b minus b. So it appears several times. So this equation is related to this map, the Adler's map. Which is the Yang-Baxter map. So you can use the symmetries of this map, and they indicate the change of variables you take, and you get a Yang-Baxter map. And a similar picture you have between the trahedral map and three large equations. For instance, the Hirota map is related to the I think total lattice equations, but I'm not entirely sure. So they are related via symmetries. That's a very nice application. And the relation of non-commutative such maps with several important lattice equations. So now we'll show you how one can, well, I promised to show how the local n-1 equation is related to the simplex equation. So here I will show you how one can use the local Yang-Baxter equation to produce solutions for the trahedral equation. So you can start with this 2x2 map. X is an element of the set, and you define these 3x3 extensions. So the 3x3 extensions are defined like that. So the indices 1 and 2 mean that the elements of this matrix sit on the intersections of the first and the second row with the first and the second column. And the rest are defined like this. So 2 and 3, that means that intersections of the second and the second column with the second and the third row, you have these elements of this matrix, A, B, C, D. So these matrices you can write that depend on X explicitly, yes? So you can substitute to this equation, and the statement is the following, that if you substitute to this equation, you will get a set of equations, a system of polynomial equations. So if the system of equations has a unique solution for u and v and w, then you define a map like that takes x, y, and z and gives you three functions of u, v, and w. So if this a unique solution, in other words, if this relation is equivalent to this map, then this map satisfies the tetrahedron equation. This is a statement without proof, but there's no counter examples. And in that sense, we will call, since this is a matrix defactorization problem, we will call, sorry.
The question is, you write this in a certain order, you choose indices 1, 2, 1, 3, 2, 3.
Because it's a Yang-Baxter equation.
Because it's
so
same
this,
as the Yang-Baxter.
Yeah. So this is called the local Yang-Baxter equation. So between them there's not composition, it's just matrix multiplication. That's why I chose this indices. So if a map comes from this such matrix factorization problem, then we will say that this equation is a Lax representation. So in this sense, you can take a matrix 2 by 2, substitute it here. If you have a unique solution, you get a solution to the tetrahedral equation. And that's one example. So you take this matrix, a matrix depending on a variable x, and k is just a complex number. You define its 3 by 3 generalization exactly the way we said earlier. You substitute it to this equation. So if you substitute to this equation and you equate this, you get a 3 by 3 matrix here and 3 by 3 matrix. So you equate each element with each element. You get this system of equations for u, v, w, x, and y, and z. So this system has a unique solution for u, v, w. This is the solution. So the associated map is a tetrahedral map in the sense that it means that it satisfies a tetrahedral equation. And this is probably the most famous list of maps, of tetrahedral maps, is the Sarkies classifications. And here I just wrote a list of maps and the matrix generator. So this map comes from this matrix, this map from this matrix, and this map from this matrix. And the list doesn't stop here. You have this maps also, and the last one is the one I wrote in the first slides, Kasai's electric network transformation. So Kasai's map comes from this matrix. But now I'll show a new method for constructing new tetrahedral maps that do not belong to the known classification list. So look, Sergei's classification and another classification so far, all of them consider solutions of the local Yang-Baxter that uniquely satisfy the local Yang-Baxter equation. But here we will demonstrate that if we allow, if we consider also correspondences between sets that satisfy the Yang-Baxter equation, not uniquely, obviously, they also give rise to new tetrahedral maps, which don't belong to the known classification. And if we start considering correspondences, we can make a new classification of this list much wider than the known ones, and we construct way more solutions which have different, sometimes more interesting structure. So just a simple example. Let's consider this very simple matrix. So among the diagonal you have x and 1 over x. Then you consider its 3 by 3 generalizations. You substitute it to the local Yang-Baxter equation. In this case, the Yang-Baxter equation does not have a unique solution for u, v, and w as before, but it's equivalent to this system of equation. And this you can consider as a correspondence between complex field square cube and complex field square. So in order to get a map, I need to make a choice on V. If I make this choice, f equals x, then I get this map, and one can show that this is a tetrahedral map. Okay, the question is, how do I choose these variables? Most of the times I do it out of experience, but there is a way to find such, to make a choice on the solutions more formally. I'll comment on that a little bit later. And this way, we constructed these solutions with Sergei Bonin, this list of solutions. All of them come from this matrix. And none of them belong to this Sergei's classification. That's one list, and they share this invariance. And that's another list of maps that come.
First question is, when you have different maps, what you mean by different? Is there any way to map one map into another one so the equivalent maps?
I'll tell you. I think this is the inverse of this, but there's no way to go from here. So this from those two are different maps. This is an inverse of this, and this is an inverse of this, if I remember correctly. But at least two essentially different maps are in this list.
But what is the equivalence relation?
The equivalence relation is
just by the diagonal map.
No, it's there's some kind of similarity relation. So you have a function phi, and you have phi Cartesian product with phi minus 1 times the map times phi. If this is equivalent to these maps are equivalent.
But you replace the diagonal action of the map on the 3/4 of
and that's a second list that are generated from this matrix. That's the simplest example, actually. There are way more solutions that come from correspondences. So if you substitute this map here, you get a correspondence, and for particular choices, you get these maps. However, all these maps are linearizable, and it's obvious. Like if you change x, well, the logarithm of this is a sum of ln. So actually, if you change x to the e to the power x, and y to the e to the power y, and z to the e to the power y, and the u to the e to the power u, you can linearize this map. You can get a linear map, and these linear maps actually appear in a work of Hietarinta, where he studied linear maps, but without their Lax representation. But there is a way to start with these maps and get non-linearizable maps, but you need to go to the non-commutative case. So consider that X to be a non-commutative group. You can construct these non-commutative, non-linearizable maps. Then starting from this matrix here, X and X to the power minus 1. Well, this is a non-commutative map on groups, but what is not explicitly said is technically, in order to construct them, we extend the non-commutative group to a non-commutative ring. Because how to construct this? You substitute this map to this equation here, so there is multiplication of matrix, so addition is also needed. So technically, we start from a non-commutative group, we extend to a non-commutative ring to do the calculations, and then the result is a map on non-commutative ring group. So these are also solutions to the tetrahedron equation. And these are also coming from this matrix. You can also get solutions on rings. You can start by a division ring together with its center. We get this matrix. This matrix is not arbitrarily chosen. It's a Darboux matrix for NLS, which is in our old work with Sasha and Paulos Xentidis. So degenerated one. So if you start with this matrix, which is related to the NLS equation, you substitute to the local Yang-Baxter equation. Again, you get this correspondence. So now you make, if you choose U1 to be Y1, and also you can get some expressions for fully non-commutative, but if you want to make your life easier, if you assume that all the variables with indices 1 belong to the center of the ring, and actually this procedure is called centralization in the terminology of Yang-Baxter. So if you assume that all the indices 1 belong to the center, you can construct this tetrahedron map on rings with this invariance.
So Tiris,
yeah.
may I ask a simple question? If in the commutative case,
yeah.
So you make some arbitrary choices, it's like art of choices. But if you just assume that your letter is kind of rational function of all
you can.
things,
yes.
you substitute and request that can you determine this rational function?
You mean instead of
making this arbitrary choice?
Instead of this choice to make some rational function?
Rational function of
yes,
other variables,
and
then impose the condition that the map is.
So you can, well, not add arbitrary equations, but you can think of the particular symmetries you need, and you can add equations that you they could also guarantee first integrals, and you can also add equations that they can guarantee Poisson structures. So all the choices made are based on some kind of aim, general aim. But when you say simple choices like that, this one I will explain why in a few slides. I will explain the simple choices, but the more complicated choices, and we have more examples like that, is to add equations that will guarantee first integrals or Poisson structure. But in the commutative case, so in the non-commutative case, we usually go for simple choices. So you get this tetrahedron map, and well, it's non-commutative in the sense that all the variables with index 2 are fully non-commutative, but the ones are commutative. But if you want to get fully non-commutative, you can restrict this map to the invariant leaves. And you actually, if you do that and you rename the variables, you get exactly non-commutative version of one of Sergei's map. I don't remember which one is this, but it's one of the Sergey's lists. Okay, the natural question arises, how to prove that a non-commutative tetrahedral map is a tetrahedral map? Because in the commutative case, you just put on the computer and you just check straight on the question, but computer is very difficult to make such calculation. So you have this statement. So it was in 2009 there was a statement from Lucas and Papageorgiou, so that if you have a Yang-Baxter map that comes from matrix defactorization problem, this map is a Yang-Baxter map if the matrix 3 factorization implies the unique solution. And that's actually the generalization of this proposition to the case of tetrahedral maps. So if you have a map satisfying the local Yang-Baxter equation, how can you prove that this this map is a tetrahedral map? If you consider the matrix 6 factorization, I will explain what these 4 indices are. The indices 4 are 4 generalization of the matrix L. I'll show you in a particular example. So if this equation implies a trivial solution, then you can prove that this is a tetrahedral map. The proof, I did it algebraically, but I must say that a very similar statement was proved very beautifully by my friends Dimitar Daif, Boris Byshkov, and Anton Kazakov. I think that was the author, yeah? Using graph theory. It was proven using graph theory. And that's an example. So you get this matrix, and you make the 3 by 3 generalizations. You substitute to the local Yang-Baxter equation. The above is equivalent to this system of equation, and this has a unique solution given by this. So this is not a new example. It's non-commutative Hirota map, and it appears in the work of Dalila and Kashev. I just want to show how so even that, to plug it into the tetrahedral equation is a very difficult job actually, because here you don't only have multiplication, you have also, you need to take several times compositions of this map, and it's very difficult to prove it. But instead of that, it's much easier to use with polynomial expressions and do just simple refactorization. So instead of plugging it to the equation, you do it indirectly using this theorem. You consider the 4 by 4 generalizations. You plug them to this equation, and you get this system. And you get such system that is very easy actually to show that this system, from this system, follows the trivial solution. For instance, to here, I mean, you get straight away that these r's are y and y hat and y are equal. So from here, you get straight away from that x hat and x are equal. So to answer your question about the simple choices, how do I choose them? So I get a matrix. I get a correspondence and not a map. And I want to see what variables should I choose so that I get a map. So I get the same matrix and I substitute it here. I get a system. And I see that the system does not have the unique solution. So I see what do I have to choose in order to get the unique solution. And this simple choice
is again what your kind of guesswork or whatever you know.
No, it's not guesswork. You get expressions. It's very obviously what you need to choose in order to get.
Are you sure that you look through all possible choices?
No, I don't look all possible choices, but I will come to that, and you will. I want you to understand the whole point. And one of that is part of it is actually, to be honest, I don't even do that. Actually, I know what choices to make by experience. But that's why I'm telling you that well, first of all, I demonstrated that you get way more solutions this way than the non-classification list. but instead of classifying the actual solutions where you need to make changes, choices, etc., my suggestion is to make classification of the generators. Actually, not classify the n simplex maps, but classify the solutions of the n-1 local simplex equation. And there are no choices for me. All solutions coming from one correspondent will be equivalent in a sense. And it makes sense to classify the local solutions to the local n simplex equation. And I'll show you, talk about that in a minute. Then it makes, well, the next step is to how to construct four simplex maps. First of all, what is a four simplex map? Again, we start by X to be a set. A four simplex map is a map that takes four elements, X, Y, Z, and T, gives you new functions U, V, W, and R of these elements, and this map is called the four simplex map if it satisfies the Bazanov-Stroganov equation. Sorry, I missed an H here. And these here, all the syntheses are exactly defined like before. So all of this, for instance, this I5, 6, 7 acts on a set of 10 variables, and it means that it acts on the first, the fifth, the sixth, and the seventh exactly as the map indicates. So I change the first, the fifth, the sixth, and the seventh to functions U, V, W, and R of x1, x5, x6, x7, and that's how the equation is defined. And my aim is to get the tetrahedral equation, make it local, starting from a matrix like that, and generate solutions. But the first thing is, okay, as you probably understand, this four simplex equation contains all the solutions of the homological equation, the generalization. So you can trivially extend a map, like how you can trivially extend a map. So if you have a tetrahedral map, U, V, W. So this is a three simplex map. So how you can get this is also a solution of the four simplex maps. In what sense? You get X, Y, Z, and T. This X, Y, and Z go to new U, V, W, but T remains as it is. So that's a trivial extension. So in that sense, four simplex equation contains all the solutions of the tetrahedral equation. So how do I make the tetrahedral equation local? So I get the 6 by 6 generalization of this matrix. A substitute here, and which is this equation will be, I will call it local tetrahedral equation. So this will be a generator of solutions of four simplex maps. My first aim is how to construct non-trivial extensions, starting from known examples. Of course, I can construct other solutions which are not related, which are not extensions of three simplex maps, but how can I do a non-trivial extension? So that's what I wrote on the board. This is a trivial extension of a map. How to make a non-trivial extension? Okay, how do I extend trivially in terms of matrix factorizations? Look, let me start with this matrix. So let me start with this tetrahedron map that comes from this Young-Baxter local equation via this matrix. So if I want to construct the trivial extension, what do? I just add one unity here. I just get a 3 by 3 extension of this map, I add a unity here. So in order to get a non-trivial extension, I should change that to a new variable. So consider that's the simplest extension. You can make several different extensions, but that's the simplest extension. I want to demonstrate that even the simplest extension gives non-trivial 4 simplex maps as non-trivial extensions of 3 simplex maps. So you get this map and you substitute it to the local Yang-Wechsler equation, and when to again to get the correspondence for particular values of which you define 4 simplex maps. And I will show an example. So that's Sergei's map we saw earlier. That comes from the local Yang-Wechsler equation using this matrix. So I made this 3x3 extension of this matrix as I explained earlier. And I get this matrix of x1, x2 substituted to the local tetrahedron equation. I substituted to the local tetrahedron equation. Here I missed some maps here. No, everything's here. So I substitute here and I get a correspondence. This correspondence, if I choose W2 to be T2 and W2 to be Y2, I get these maps. Again, these choices come naturally from the analogous, can come naturally from the generalization of the previous theorem, or usually you make choices that don't come naturally, but you make choices with, you add equations which are first integrals in order to make integral maps. So here you get this two non-involutive maps, which are 4 simplex maps. And using this method, you can extend all Sergei's list to non-trivial extensions, which are 4 simplex maps. And here you have this. You can use several other maps, solutions using different extensions. However, the main comment I want to repeat that I suggest that instead of classifying n simplex maps, we classify the generators, namely we classify the non-local, the solutions to the non-local equation. And some first results is this. So this theorem. So these are all the essential different solutions to the local tetrahedron equation. So all these maps that for simple facts that you saw in this talk come from generated for these matrices. So here what you can do, all the rest solutions, actually you cannot get a 4 simplex map starting for a matrix where all the elements are non-zero here. That's not going to happen. So the maximum amount of elements are 5. These are all the essential different matrices. So that's actually my student Mikhail Chekhov found these matrices. The work, actually the proof is completely computation, but would like to find, as Dimas says, the meta-Uralin, so the next level. So how come naturally they come from symmetries? So all the other solutions come either by reflection with respect to the diagonal, or if you put 0 some of them, or rearrange them. But rearrange is a little bit obvious. And in terms of reflection, you can also write how you can change the correspondences. So that in one example. So if you put this matrix to the local Yang-Wechsler equation, you'll get this set of equations. If you reflect with respect to diagonal, so x2 will come here, x1 will come here, so you get this map. And the correspondence that we'll get via the 3 simplex equation is exactly the same that we get from here via this change of variables. So u goes to w, u goes to r, v goes to w. So that's pretty much what I want to say. So I will close with a comment that we suggest here actually you can, from these matrices you can get all not only new, but you can recover all the known examples of maps in the literature, so it makes sense to classify the solutions to the non-local, to the local n-1 equations. And the next step is to classify the local solutions to the local Tetrahedron equation, and maybe we can get an indication of how to classify the solutions to the local n equation in general. So that's what I wanted to say. Thanks for the attention.
Any questions, comments?
Yes, sir.
These maps which admit tetrahedral representation, they are integrable in some sense.
Yeah, well, there is a definition for integrability for maps by the Selov. So you need to have a certain amount of, so half the dimension of the map, you have functionally independent integrals of motion, which must be in involution with respect to a Poisson bracket. Not all of them are integrable in this sense. They are integrable in the sense that they come from Lax representations, only in this sense. Not for all of them you can even find invariants. Well, that doesn't mean that they don't exist or they're not integrable. It's very difficult to show that something is not integrable. The statement is that you cannot show for all of them that are integrable.
So integrals, some of the integrals will derive from this relation.
Well, in the Yang-Baxter equation, yes, but here the thing is that you get determinants, traces, etc. But here it doesn't work because the thing is that it's not the same matrix everywhere. So you cannot derive them from the equation itself with trace and determinant with the classical schemes.
But the conjecture claims that they should be these integrals.
I believe yes, but you know, that's my opinion.
Other questions?
Could you repeat the statement about the local tetrahedral equation, about the kinds of the matrix 3 by 3?
Yes, sure. Okay, so we start with matrices that we want to classify the solutions of this form. So it's x vector, x1, x2, x3, x4, x5, x6, x7, x8, x9. To find all the solutions. So these are all the essential solutions. There are no more other than that. All the rest are obtained if you rearrange the variables, obviously, if you reflect among the diagonal, or you set 0 some of them.
But if they are dependent, one variable depends on another. So,
for
instance, you have x minus 1.
Yeah, you can go to your equation, for instance. I'll show you. So, for instance, for a simple case. So you go to the result and you change. You change. So x1 will be x. x5 will be x1 to the power minus 1. And then you go to the correspondence and you change not only the x's but the u1 goes to x, u5 goes to u1 to the power minus. You change all of them and you get exactly the same solution. In terms of correspondences again. If you go to the maths, it's different situation. So you can recover all the, well, for sure all Sergei's list.
So there should not be a solution with all non-zero coefficients?
Well, the rest, yeah. So this will be 0, this will be 0. To recover, I mean, in this particular example, in order to recover Sergei's one solution to the
No, I mean, not talking about Sergei, we're talking about just a solution.
Yeah.
So you just can you formulate your theory with all the conditions? No, because essential is not mathematical statement.
It's not mathematical formulated.
It's not mathematical, so it's not a theory.
It's not a paper. It's the top. You can ask and I will answer you. So what's the question?
No, the question is, so what is the statement? You believe or you prove that if your matrix is full and your letters may be related by somehow, whatever relations, no possible relations between, so that...
Yeah, I believe that you can construct it, yes. At least I have tried for all the known ones.
So all the known solutions are
Yes,
of this form. That's the meaning of the...
No, but here you get infinitely many more solutions. So all solutions known actually come only, most of them come from this matrix, if not all, for particular choices of the values.
Any other questions? Okay, thank you very much.
Well on time. Я как-то раньше не думал, что можно расширение. Я не раз рассказывал, что естественно, на мой взгляд, рассмотреть спектральное множество, то есть множество с решением Янгу-Бакстера. И думать там про расширение. Там прототип писали. Но это то, что делаешь, это расширение, но которое из одного делает следующее.
Смотри, надо забыть про Макс. То есть мы идем на локаль только, на локаль. Уже Макс это уже неконтролируемо, потому что если разрешать, чтобы соответствовали решениями, тогда уже, чтобы определить отображение, надо делать выборы. Их есть, конечно, много. Так что классификацию тут не сделаешь. Поэтому я просто классификацию. И тут что такая матрица.
И это, конечно, очень симпатично, это очень напоминает
вот эти системы еще, я помню, похожи я пришлю тебе, может, ты еще расскажешь. Хорошо, да,
выбирать не память.
Конечно.
Конференции идут, кстати, председатели.
Да, но знаешь, то есть вот это было не супер сложно. У ребенка была вот такая идея, что вместо просто тут поставить вот такие. Потому что у нас есть умножение между ними, и там какое-то соотношение. На самом деле получается, что я пробовал, пока не для всех, что мне известно, можно замену сделать здесь. Например, вот это x1, ставишь сюда x1 и x2, без проблем, и работает. Но самое сложное, там делать вот это для local differentiability. Там нужно обойти это.
Кстати, скажи, пожалуйста, если брать решение какого-то такого типа, делать с ним преобразование, эквивалентности, да? Вот диагональное преобразование по каждому особенно. Во что? То есть можно сказать, что там к какому-то каноническому виду это приводится?
Вот это не канонические.
Можно ли его еще возвращать эквивалентность?
Да, я не могу сказать.
Ну, просто это естественная задача. Если ты говоришь, что бывают такого типа, как еще можно упрощать, какие между ними есть трансформации?
Между ними нет. Это тоже нет между ними. То есть никакой similarity, никакое изменение. Но наш доказатель это просто чисто Должно быть симметрии, должно быть формально объяснение. Это то, что
Ну и вот, как бы, если просто взять общее, 9 элементов, как это упрощать? Какими преобразованиями можно упрощать?
Я думал, что упростить не... просто занулить.
Нет,
да, я понимаю.
делать какие-то преобразования подобия, которые упрощают.
Да, они не связаны между преобразованиями. Да.
Вот берешь общее с 9 элементами, не нулевые. До чего можно упростить? Можно ли единицу поставить?
Да, и это можно, но единственный момент, что смотри, если тут в случае отображения Янга-Бакстера, который происходит без уравнений, да? Тут если брать L и его преобразование подобия,
да.
Вот это удовлетворяет этому уравнению, а вот это тут неправда. Так что это в принципе можно посмотреть, но не будет удовлетворять уравнение потом.
Подумать, как это модифицировать. Ну, то есть, естественно, стоит задача классификации.
Задача классификации, значит, у нас должно быть отношение эквивалентности какое-то. Да.
Нет, окей, хорошо, это не такой вид классификации, как все остальные классификации. То есть у Адлера момента что там нет эквивалентности.
Ну как нет?
Нет, но там есть, но не во всех.
Рациональные, так сказать.
Мой плюс преобразование, да.
Ну, хотелось бы, так сказать, понять, так сказать, что, какие преобразования возможны, так сказать, и каких как-то, так сказать, авторизоваться по ним, потому что иначе задача необъятная. И говоришь, что
по каждой переменной делается рациональный процесс.
Ну почему по каждой? Может быть, можно и не по каждой, а может быть, можно сделать просто рациональное, так сказать, преобразование общее.
Нет, это я понимаю, то есть в принципе, equivalency relation у меня такого нет. Я просто мое определение эквивалентности, но это не соотношение от эквивалентности, которые 1, 2, 3, что все решения, все отображения, которые происходят из одного корреспонденса, они эквивалентны. В таком смысле, что у них общий генератор. Может быть, плохая классификация, плохая, но тут смысл такой, что все возможные решения происходят из этих матриц. Можно, конечно, не назвать классификацией, но это факт. Кстати, я могу сказать, я уже могу сказать, например, одну вещь, про которую, то есть это тоже могу сказать, что покрывает все матрицы, где соотношения между ними они рациональны. А если электрические функции, то это уже другое. Нам это вообще я не знал, там вывод не сделается.
Такое ощущение, что не дожали немножко, так сказать, это самое.
Это начало, но очень хорошее.
Нет. Начало состоит в том, что представлено много решений. Да. Много решений. То есть,
нет, это 1, 2, 3, 4. Много. И все.
Больше 3 много по-русски.
Ну почему? Там же еще будут эквивалентности, которые можно разрешать по-разному. Так сказать, то есть не эквивалентности, как их называется, корреспонденс, как вы называете, да? Которые по-разному, поэтому, так сказать, их не 4, а больше. Вот. Теперь, значит,
больше соответствует отображению. Я хочу понять решение только локаль. Там никаких отображений нет. Там чистое, как называется, просто каждую матрицу соответствует какое-то алгебрейское многообразие. И все. Нет, список полиномиальных уравнений.
Ну, там вообще, наверное, рассматривать задачу информизации этой штуки. Потому что тот корреспонденс, который он делает, это один из частных информизации. Вообще, говоря, задачу можно общую поставить информизации. Это рациональная информизация или какой-то.
Я не утвердил, что нельзя того сделать.
Просто
наоборот сказал, что это...
найдено много решений, а хотелось бы понять...
Конечно, много. Я сказал, что это первый результат, но раз в литературе нет ничего, это первый результат. Не сказал, что это да, может быть классификация даже плохое слово. Я не утверждал, что я решил проблему симплекс уравнения.
Нет, ну то, что найдено новое решение, это уже замечательно. Ну, так сказать, здесь вопросов совершенно нет.
Нет, но
вопрос есть о том...
но есть некоторые шаги, чтобы показать людям, надо ждать, пока будет классификация, что да, вот уже показал, уже начинает обсуждать. Может быть...
Ну хорошо,
да,
ладно, это самое, я на самом деле доволен вашим выступлением, то, что делается. Другое дело, что все равно остается какое-то такое чувство, что не до определенности, так сказать. Ну, то есть вот есть масса вопросов, на которые хотелось бы ответить.
Ну, я не могу на все пока вопросы ответить, но можно обсудить.
Ну да, то есть вот, мне не очень понятно утверждение, что невозможно сделать, так сказать, чтобы вся матрица была полная.
Да, ну я объясню, то есть если вот это не любые элементы, не имеет решения, не удовлетворяет уравнению локальных трахидон.
Ну, эти буквы могут быть зависимыми, то есть вы считаете, что буквы независимые, а буквы могут быть зависимыми.
Хорошо, да, я с этим согласен. Да.
А если они зависимы, то у вас нет этого утверждения?
Нет такого утверждения, это правда. Утверждение только, но счастье, что из этих можно реконстракт известные, но да, если разрешить между собой зависимость, но это тоже не совсем уверен, потому что там ограничиваем уже еще больше, тут больше свободы. Я думаю, что на самом деле не будет, если будет между ними соотношение, потому что это более ограниченная задача. То если не имеет решения так много свободы, может быть, ну ладно, хорошо, я, может быть,
А какое-нибудь теорию возмущения нельзя сделать, там, например, взять какое-то там решение и его возмущать, так сказать, сводить задачу к линейной?
Да, можно, то есть, в принципе...
То есть я бы, так сказать, мог бы начать с какой-то, ну, то есть у нас есть какое-то тривиальное отображение, ну как единичное, потом мы его возмутили, так сказать, у нас возникла линейная задача.
But then I tried the same for tetrahedron and you get trivial maps. It's not that I mean for the Young-Baxter map, you are thinking about the header that you made this linearization, but the same linearization if you substitute to the local Young-Baxter equation the same matrix, you will get only the trivial map. And then I thought, okay, maybe, I don't know, then I stopped thinking about linearization. But
perturbation theory from какого-то решения мы могли линейно посмотреть поправку и так далее, что-то вырастет, то есть пусть это будет не рациональный, не полиномиальный, какие-то в виде формальных рядов.
Ну, я пока не понимаю все-таки вот алгебраически, что...
Мне непонятно вопрос, так сказать, какие есть, ну, калибровочные там какие-то степени свободы, то есть вот не такие тривиальные, которые мы, так сказать, представляем, а может быть тут больше есть какие-то...
Саша, это глубокий вопрос. Вот даже для уравнения Янга-Бакстера есть тривиальный подход, это когда вы по каждой компоненте, Ян-Бакстер метод, да, отображение Ян-Бакстера, вы можете каждую компоненту менять одним преобразованием множества, на котором все живет.
Да.
Вот, но вроде бы это бедная симметрия. А вот есть такое понятие гитарное отображение. Оно утверждает следующее, что, по-моему, по любому невырожденному решению уравнения Янга-Бакстера, Ян-Бакстер мэп, можно построить эквивалентный ему, который на одну ногу действует тривиально. А во второй возникает вот эта вот квантовая операция. Но это преобразование, которое затрагивает сразу все косы. То есть оно переплетает действия всей группы кос таким общим преобразованием, но сильно упрощает каждое преобразование в отдельности. Вот, ну, я сатирисую, Сережа об этом рассказывал.
Здесь вот, ну, может быть, то, что аналогично. Да.
А тут может быть еще интереснее, потому что вот мы рассматриваем уже локальное уравнение тетраэдров, а у них везде часто, вот они пытаются их строить из локального решения Янга-Бакстера. Вот, и тут можно использовать чуть большую симметрию решения уравнения Янга-Бакстера. Ну, то есть вот как бы эти гитарные отображения, может быть, сразу не на всем, а только на частях. Вот, но это надо копать, это совершенно не проработанный сюжет.
Ну и еще, так сказать, они, как говорится, работают с уравнением Янга-Бакстера. Почему-то матрица всегда у них там 2 на 2. В принципе, так сказать, никто нас этим не ограничивает, и можно, так сказать, там у нас есть вообще большие свободы.
Это естественно 2 на 2. Потому что нужна вот эта вот факторизация, единственность факторизации произведения 3 элементов.
Что, если мы сделаем блочным?
Там меньше шансов, что будет единственность. Просто вот отличный пример единственности факторизации — это ортогональная группа. В ортогональной группе есть углы Эйлера. Они однозначно определяются. И вот, но единственное, нужно их в 2 порядках определять. И вот преобразование из одних в другие это решение уравнения тетраэдров. Это вот и есть то решение уравнения тетраэдров, которое связано с локальным уравнением Янга-Бакстера, у которой здесь есть групповое объяснение. Мы в 3 на 3 матрице взяли трехмерную группу, и в ней есть разложение в 3 однопараметрические подгруппы.
А что, если мы взяли там другую СО4, так нельзя сделать?
Вот в СО4 она шестимерная.
Да. Она вообще сумма 2 трехмерных прямая. СО4 она же не простая, это есть, конечно.
В смысле алгебра, да?
Даже алгебра это прямая сумма, так сказать, СО4, СО3.
Простите, пожалуйста, а вы не в курсе, где обедают участники? Вы не решили не присоединяться к общему? Где-то там, где-то в казенном месте нас кормят, где-то не на территории.
Не знаю. Вчера где-то их кормили, кстати.
Ну ладно.
Ну, в общем, то есть, как набор примеров, это, конечно, очень хорошо, но, так сказать, наука точно.
Фундаментально тут пока еще
фундаментально еще пока не понравился.
Ну да. Но это надо работать. Сережа, они все-таки примерами увлечены.
Да.
Нет, Сережа тоже
Сережа грамотный человек.
Но он выступает против всех систематизаций. То есть я много разных идей предлагал, мы регулярно встречаемся. Сережа, он очень консервативный, несмотря на то, что профессиональный.
Нет, ну, так сказать, меня немножко иначе учили.
И, конечно, вот есть пример, надо сразу пытаться угадывать, какие здесь симметрии, какие калибровочные преобразования.
Да.
Да, разумеется. Но вот на самом деле вот этот следующий слайд, он интересен.
Нет, ну а следующий слайд, что он интересен, так сказать, что у них есть некие преобразования этих матриц, которые приводят к преобразованию
контролируемые. И вот я сатирису уже сказал, что это очень близко к идеологии кластерных преобразований. Так что если удастся здесь какой-то тоже заметить.
Нет, ну хорошо, что есть масса примеров, но об этом можно думать.
Ну что, как насчет параметра возмущения?
Параметр возмущения надо. Как это? Отжиг. Нет, ну Саша что говорит, что хорошо бы относительно какого-то решения пытаться искать возмущение, как у локального уравнения, так и уже у
Ну, который не будет обязательно решением, да?
Ну, понятно, да.
Это первое. Второе, значит, меня еще это самое, вот эту идею моих идеалов, так сказать, сюда можно теперь запросто притянуть, потому что надо, чтобы при отображении идеал отображался в себя, и тогда, значит, у нас возникнут квантовые эти самые штуки. Вот эту задачу
можешь спросить, то есть, почему я хотел спросить последний раз после нашего семинара. Для отображения хорошо, для таких, которые происходят из матричной квантизации. То есть берем результат, да, и стараемся делать квантизацию. То есть найти такие как сказать, да, для которых для которых есть полосовая структура, для которых
нет, полосовую структуру можно потом найти.
Янг-Бакс, что она остается Янг-Бакс.
Нет, вот у нас есть идеал, у нас есть соотношение. Значит, эти соотношения порождают идеал. Значит, мы что делаем? Мы делаем наше отображение. Так? Когда мы сделали отображение, значит, наши лупочки стали другими, так сказать, теми самыми. Мы их подставили туда. Значит, у нас возник другой полином, да? Вот так, да? И этот полином должен быть равен нулю в силу того полинома, который был. То есть, что идеал перешел в идеал. Что, так сказать, вот некие соотношения, они не то чтобы инвариантны, как вот первые интегралы. Это более слабое свойство, чем инвариантность первых интегралов. Они не инвариантны, но как множество, так сказать, которое они определяют, оно, так сказать, само множество, оно инвариантно. Вот так.
Есть какой-то способ, не знаю, то есть использовать, чтобы само представление лекции указывало, что, как выбрать эти соотношения. То есть я скажу один момент, который не связан с этим, но можно какая-то идея оттуда. То есть, например, у нас есть отображение Янга-Бакстера, и можно тут стараться найти некоммутативную версию самого отображения. А если есть представление лекции, что делаем? Просто начинаем с того, что считаем, что элементы не коммутируют, а потом, если поставить представление лекции, оно само даст правильную некоммутативную версию. Можно как-то, не знаю, совместить с представлением лекции?
Можно достать? Что ты хочешь сказать? Я мысли не уловил.
Я хочу сказать, что... Нет, это я говорю, что никак не связано с тем, что говорит Саша, но может как-то из этого, не знаю, как-то постараться получить такую идею. То есть у нас есть отображение вот это. Самое простое Адлера. Это плохо.
Кстати, насчет отображения Адлера у меня есть вопрос интересный. А вот оно на неабелевый случай переносится?
Конечно, но поэтому я сказал плохой пример, потому что это очень простое.
Нет, не очень простое. Дело в том, что в неабелевом случае, садись. В неабелевом случае f неабелево, не коммутирует, правильно?
Да.
Это не коммутирует, не коммутирующий, не коммутирующий. Почему А и Б коммутирующие? Почему они пропорциональны единичной матрице?
Это, да.
А она может быть тоже не коммутирующей?
А, Б не коммутирует. Обычно принято сразу А и Б
делать коммутирующие. А почему они коммутируют?
Я могу сказать, например, что я пробовал бывает момент, где, чтобы решить, надо предполагать, что они коммутируют.
Ну да, но я говорю, что в принципе, так сказать, я почему говорю, вот сейчас вот мы с Буштабером как раз обсуждали, когда пишется, ну вот это уравнение Норрикса, например, да, то говорим, что мы берем, например, картелек, да, а потом этот
ответ на неопределенный. Потом мы его интегрируем. И говорим, что это константа. И это есть константа, которая в кривой константе. Правильно? И эта константа, вообще говоря, может быть не коммутирующей. И если их брать не коммутирующие, то оказывается удивительно, что их там, ну, то есть их много не коммутирующих констант. То есть кривая, которая получается, у нее все буквочки между собой не коммутируют. Ну, вот я почему спрашивал про эти самые спектральные кривые Дня. Вот. А между ними есть коммутационное соотношение квантовое. Вот. То есть вот в этом направлении. Так это здесь примерно то же самое.
Да, что здесь на самом деле не мешает, потому что там стоит минус между ними, а не умножить.
Правильно, но потом-то мы делим. А когда мы делим слева или справа?
Или справа, хорошо, я понял.
Ну, потому что...
Да, конечно.
Нет, это вполне такой законный вопрос, на самом деле. И это расширяет возможности колоссально, потому что отсюда возникают вот эти самые бигамильтоновские системы, там бигквантование, оно оттуда возникает, потому что эти буквочки не коммутируют. Потому что если у нас что-то есть, так сказать, раньше мы говорили, что это константа, мы одни буквочки говорим, что не коммутирующие, а вторые вдруг мы, так сказать, и вы сразу резко, так сказать, изменили задачу и сократили, так сказать, возможности. Нет, может быть, они и коммутируют, но это можно получить законным путем. То есть вот можно просто, как говорится, взять и посмотреть, какие стабильные идеалы. Так сказать. И может оказаться, что стабильный идеал только тогда, когда она коммутирует. Нет, вообще это все очень интересно.
Я постараюсь объяснить вот эту идею. То есть, например, есть вот такое отображение, то есть просто тривиальное. И возникает вопрос, какая правильно вот это, удовлетворяет ли вот это, либо, как сказать, либо поменять порядок между x минус 1 и y. Возникает вопрос, как правильно делать некоммутативные варианты. И есть способ это сделать. Это какой способ? Но просто люди стараются, то есть пишут какой-то, ну может быть, типа такой, но у Франка был в старой работе. И находят код, для которого это остается отображением Янга-Бакстера. И тут надо просто, это большая работа, чтобы понять, если правильно ли это. Но если другое, если у этого есть тривиальная параллакс, но скорее всего это вот такая параллакс, вот это. Да? Это происходит через задачу матрицы факторизации. Вместо стараться отсюда понять, как отсюда пойти сюда, некоммутативная версия, идем опять сюда и думаем, что они не коммутативные. А если коммутативные, вот эта симметрия задач даст правильную некоммутативную версию. Можно ли как-то вот эту квантизацию как-то, чтобы презентация лакса помогла сделать?
Ну, это, так сказать, законный вопрос. На самом деле это даже в каком-то смысле было бы лучше, потому что когда мы имеем полиномы, с полиномами мы легко, так сказать, мы пишем, так сказать, идеалы, и там все легко работает. А когда нам надо что-то делить, то здесь уже нужно иметь некую аккуратность в этом.
Может быть, тогда все-таки работа опять с локал уравнениями, с локалем лакса.
Кстати, этот вопрос на твою деятельность распространяется. Вот ты написал кратительный аналог какого-нибудь известного уравнения.
Да.
У него представление лакса выживает.
Да, выживает. Ну, выживает. Представление лакса выживает. Другое дело, что там есть свои сложности, например, поскольку в этом мире перестает присутствовать там трейсы и все на свете, то есть там надо некую другую жизнь, так сказать, устраивать. Но есть интересные вещи там, в общем. Нет, представление лакса есть. Представление лакса есть, но что с ним сделать? Он у тебя на свободной алгебре, а потом ты можешь туда, как говорится, раз у тебя все совместно, там просто идеалы накладываем.
То есть, соответственно, твой вопрос положительный ответ, что вся эта деформация, она пропускается через представление.
Да, она пропускается через представление.
Значит, и здесь тоже разумно его
тогда
искать.
Нет, у нас дело в том, что мы наоборот, что у нас обычно наше отображение происходит из представления лексика, как что-то плюс.
Нет, ну, я думаю, что мы, может быть, к этому вопросу вернемся, даже если я уеду обратно в Англию, потому что меня, честно говоря, отображение очень интересует, и хотелось бы добиться вот эту технологию, а кроме того, с этой технологией автоматически возникает, дело в том, что мы не предполагаем никакой постслоновой структуры, она возникает. Просто, так сказать, вот здесь
Это симметрия, конечно, свойство, это сильное свойство, что она есть.
Она есть, да. И тогда, так сказать, ну, можно было бы, так сказать, говорить об интегрируемости и всего на свете. То есть это... В общем, давайте мы к этому вопросу как-то вернемся. Ну, и у нас...
можно, в принципе, на следующий... конференции только...
Я не буду.
Четвертого, давайте планировать. Онлайн, не онлайн, как получится.
Чего 4?
4 октября, в среду.
4 октября, в среду я лечу через Турцию с утра целый день и прилетаю поздно.
в Турции в аэропорту очень скучно.
В Турции нет интернета.
А где же эти талончики на полчаса там?
Слушай, у меня кто-то ездил через Литву.
Через Литву, я знаю, ездят люди, а кто? Сергей Смирнов есть. Сюда и обратно.
То есть из Вильнюса билет стоит на 15 тысяч.
Ну, в общем, недорого стоит.
А до Литвы можно доехать на поезде.
Отсюда, да?
Самый дешевый, кстати, в Европу на света было Москва, Питер, Хельсинки.
Ну да, нет, я смотрел это, но, как говорится, я-то могу, а у меня британский паспорт. А так как попробуй через Европу проехать, так сказать, это же еще надо иметь шенгенскую визу.
Скоро может быть трудно будет забраться.
А? Что ты говоришь?
Что, может быть, скоро, может быть, и понадобится из-за Брексита иметь шенгенскую визу.
Не знаю.
Нет, я не знаю такого. Ну ладно, хорошо, тогда увидимся на следующей неделе, да? Ладно, все, давай на 16.
Ну ладно, увидимся. Ты точно не видел? Нет, я
перед докладом постишься. Ну да, тебе сразу задают вопросы, ты такой, мотивация бросал через метро. Там, кстати, кофе есть вроде для участников конференции бесплатно. Вот, тут, короче, прикол. Ну, вот есть такой День, я не знаю, знаешь ты его или нет, по-моему, он цитируется то ли студент, то ли поток, ну, в смысле, был сейчас у меня выпустился. И он, короче, предлагает, в принципе, следующую идею.
I'm not an expert in Newton.
Yeah, I'm not the one.
No, I think I'm okay. I think it's a good idea not to try too many things because it will make me panic.
Okay.
No, I'm kidding. But do you want a coffee?
No. Вот. А еще я сейчас за ланчем, значит, познакомился с китайцем, который, вот, его, может, знаешь, может, нет, в общем, зовут Сяо Ли Лиу. Вот. И он говорит, что они, в частности, доказали вот эту Геометрическую формулу про суперинтегрируемость Концевича, Александровскую про эту Богровую модель, все такое. Но это вот какой-то, это не фан Лиу, это какой-то...
Не, я знаю, как это.
Знаешь, да?
Лично не знаю, но
вот, я сказал, что, ну, возможно, что-то там, но я как бы сам... То есть он явно, да, про тоже как бы самое умное. Вот, вообще очень получается все легко и просто доказывает, что вот это ПГВ, короче говоря, доказывает вообще на одну страничку интегрируемость.
Ну, да, я тоже знаю. Если даже действительно строчку более нормально.
Можно выбирать ПГВ?
Ну да, там очень простая. А вот в случае с этим женщин, у них, конечно, доказательство есть, но оно не такое, как хотелось бы. Ну, в том смысле, что оно условное. Насколько, ну, по крайней мере, может, последнее не видел текст, но как-то так были. Ну, проще найти в этих ссылках на нас.
Вот как мне сразу не понравился интерфейс.
Вы решаетесь.
Да, нет, я ищу все время в этом архиве просто так. И вот тут вот, значит, нужно Google Scholar цитировать 7. Это правда one rank. Так, это потому что не та. Вот.
У него по 7 8. Но они же здесь застряли. Может сейчас пошли.
Еще он сказал, значит, почему-то, что вот он считает, что если веросоры добавить лишь достаточно хорошо. Я думаю, что мы там на первого еще знаем, кто пополам, а как мы 20-го уже ну, нет, так, а как написать конкретно?
Здравствуйте,
форм.
А,
ты имеешь в виду расходы, да?
Конечно, это ВВП, это чуть сложнее.
Да.
Собственно, у них поэтому и там статьи целые с формулами. Формулы, в принципе, все, тем не менее, бесконечные. Просто, на мой вкус, там...
Погоди. Вот мы знаем всякие формулы, но в лучшем случае в этом байосе P, мы их и так знали. В смысле, что там P, это как бы не байосе шуров.
Байос шуров, мы говорим о шуров.
Да, и он коэффициент сложный.
Мы с тобой даем.
То есть как бы...
Они просто... Если это помочь.
То есть система Верофора, она выглядит как сумма, потому что вы выдавали типа прибавить
Я скажу, пусть оставит.
n коробок, и какой-то коэффициент.
Ну, это коэффициент узнаваемый очень. Он же мешает основным типом.
Да,
формулы можно... Там единственное существует проблема, что типа, поскольку там, например, для рядла добавлять 2 коробки, но коэффициент там такой, что типа для каждой коробки он вот аргументная функция. Поэтому там ответом равноправие между простым для 2 коробок. И поэтому там важно, типа, какие коробки ты добавляешь. В этом формула очень усложняется, потому что нужно писать, что там один коэффициент добавляешь, другой коэффициент и так далее.
Сейчас, почему? То есть, если для каждой
ну, в чем? Кто-то наверху сидит. Если ты можешь их прямо функции написать, там у тебя, я не помню, у нас там может быть сейчас, то есть условно для каждой коробки 460 грамм там на x
сейчас, и это и есть байт шуров. В этом смысле.
Нет, чисто формула байт шуров это двойственность на действие. Эти коэффициенты.
Ага.
Просто теперь у тебя прикол такой, что допустим, слишком много вкладов. Надо добавить теперь, когда у тебя, если не ошибаюсь, когда у тебя 2 коробки, ну, прикол в том, что Версор добавляет 2 коробки. Поэтому, в принципе, не так важно, какой коэффициент для одной. Важно произведение. И она при этом добавляет либо вот для соседних, когда у тебя x чисто равны, здесь она добавляет вот так.
Да. Либо x функция.
Да, это очень надо сделать. Это вот это равно. Минус вот это. Ну, то есть вот эта вот функция чуть-чуть зависит от того, так,
Можно вечером это сколько у нас?
Ну, в принципе, если вы считаете за математику, это совсем не важно.
Функции вообще можно как-то написать, да. Просто как бы, если хочешь красивую форму, у тебя просто раньше была формула, что у тебя не важно, как ты коробка управляется, у тебя как бы произведение. Просто теперь, если хочешь написать ее не чередом функции, а как еще с полиномом, то уже начать, что у тебя бывает случай такой классный, наверное, сумма не по 2 варианта коробки, но сумма по пару.
Но при этом они обязательно либо одна по другой идут. Нет, они еще уже могут быть вот так. Или это не
Вот, насколько я помню, так не может быть. Они немножко так.
Это вот эти расследные пункты, что ли?
Ну, для джаков, естественно, сложнее. Ну вот, но нет, но для шуров, конечно, сложнее. Мне это нравится, очень написать. Ну, они
Максим хотел, более-менее. Максим от меня хотел, что вот берем голосовую, начинается действие,
и теперь это, ну, то есть, через ваши выражения, даже вынуждены решение всех, но это разбираться сложнее, это очень технически. Если на вашем коде все подписывается, там смс, ну, весь текст, он просто сообщение доказывает.
Что надо просто забросить вариант все.
Ну, тоже, видимо, какая-то такая...
Ну, то есть это, ну, как бы, кто-то хотел бы угадать вариант.
Пока самому это хочется для себя что-то понравится.
Ну,
нет, типа задумка в том, что ну, действительно, что исходная картинка была такая, то есть единственное, все преподаватели мы заштриковать себе, знаешь, как типа в теории поля рисуют.
Да.
Полностью ставят. И вот на фоне, ну, так написано, просто хочется, чтобы весь фон был прозрачный, но при этом вот эти, ну, там типа какие-то безумные нарисованы. Но прозрачно, так, чтобы они как бы совсем типа, не на первом плане, ну, что рисник на первом плане, но при этом
Зачем?
слишком неправильно. Вот, а так, чтобы основной темой было вот это, что эти визуальные, за один план.
Они его знают, наверное, скажут. А что, оно как бы как раз вписывается в этот похожий формат. Погоди. По-моему, тут тоже есть какое-то. Да, интегрируемость. Да, там такой большой корабль, маленький крен, а это тоже большой корабль.
Наши встречи, наши курсники не будут проходить в новых ощущениях.
Если напишут, тогда получается намного хорошо. Ну да. Вот открыл демонстрацию. Надо зарегистрироваться. Для этого как
Значит, это может быть, конечно, психологический эффект, но ожидается же реально.
Все нормально. Ребята. Вот, смотрю, сам минуту поставил суп, и все кипит практически. Ну, горячий, вот прям нельзя, а суп просто холодный. Потом, как его достал с холодильника, такой. Это психологический эффект. Научный феномен.
Ну да, просто антинаучный. Ну, возможно, если это объяснить, то будет вот примерно что выступление. Да, ну тут такое, знаете, ну там, если вы душат, когда они там что-то делают. Я уж не помню, что.
Надо, что именно должно быть как бы оправдаться, потому что должно быть точно наоборот. Ну как бы по моей логике.
Нет, ну смотри, оно может быть как бы довольно, ну то есть в чем разница, да? То есть если макароны, вода распределена полностью по объему, она перемежена какими-то кусочками воды.
То есть да, как мысль в том, что воды, короче, большая теплоемкость.
Ну не только.
И типа, молекулы, и короче, когда ты например, что-то реально сделаешь совершенно количество молекул воды, они сближаются с соседними молекулами, как бы ты даешь типа все сразу, ты суммарно типа рамкость, потом средний, потом сейчас как
когда у тебя большое тело воды, да, то она этими микроволнами вот так колеблется синхронно. Поэтому она собирается, она нагревается, она делает дефект, она берется оценки и нагревает.
такая версия тоже.
Да, выпить молекулу воды, но просто не видишь внутри.
Главное, что они должны типа иметь как бы возможность с чем-то параллелизироваться, с чем-то.
Да.
Ну, в общем-то,
следующая задача размешать
А вы Виктор, да? Ну вот сейчас я его скачал на флешку, сейчас ее перепишу.
А, ну что, могу обладать как-то знанием, как бороться. В чем? Я загрузила, как дальше. Как иконку сделать побольше, при этом, чтобы она листала. А, вы другую программу надо использовать, что ли?
Вот это.
А, ну вот это вот, да. Вот это по фону, да.
То есть если вот это, if you need to use bug, then I think...
Ну ладно. А видите, а вот пальцы нельзя вытянуть, вот эту штучку, да? А пальцы можно тоже? Можно. Попробуйте. Видите? А,
Да. Оно исчезает со временем, это меню?
Нет, если нажмешь где-нибудь, то исчезает.
Сейчас, да, она
так, то есть нажимать надо только туда, получается. Смахивать. И нажимать обязательно вот сюда, да?
Ну, в общем, да.
Хорошо. А если исчезнет, то надо вот здесь. А это...
Ну, это, в принципе, не нужно, да, можно пальцем. Да, я очень извиняюсь, у меня сейчас преподавание, я уйду. Yeah, and then after that, you go to the after this. Yeah, and when after just before the next one. Signal much.
So the first speaker of this afternoon is Professor Yakov, and he will talk about commutative subalgebras in the GL1 hat, Youngin, and the matrix model.
Thank you so much. I'm not a professor yet, but I hope to become one at some point. Okay, good afternoon, everybody. My name is Viktor Mishnikov. I'm going to talk about commutative subalgebras in the affine GL1 Youngian and its connection to matrix models. I'm going to explain a few results that we obtained together with Alexey Morozov, Andrei Mironov, Alexander Popolitov, who is also here, and myself. Okay, so let me start. Okay, it works. So let me just briefly state the results right away. I would like to argue that the study of the superintegrability property of matrix models and its relation to the W representation of matrix models naturally leads to a description of some commutative subalgebras in the affine Youngian, so the Youngian of GL1 hat. So I'll start with a basic review. I'll review the Gaussian matrix model and try to introduce all the concepts on this example. And I'll try to explain what is superintegrability of matrix models. So then I'll proceed to the description of W operators and the W1 plus infinity algebra. And finally, I'm going to talk about the beta deformation, which will lead to the deformation of the W1 plus infinity algebra and to the commutative subalgebras of the Youngian. So let's start with matrix models. When we deal with matrix models, we deal with integrals of schematically the following form. So we integrate over some space of matrices. I'll focus on Hermitian matrix models. So it's going to be the space of Hermitian matrices. We choose some potential, and so usually we include a generated function of all invariant polynomials
So, and the partition function. So this integral is called the partition function, and it's going to depend on these parameters pk, which are called coupling constants or time variables, depending on the context. So this should be understood perturbatively in pk. So we expand this formally under the integral, and this partition function is a formal series that is a generating function for various averages of invariant polynomials of this matrix. So there are a few important features of matrix models that are going to be important during my talk. So first is the set of Virasoro constraints, which is which follows from the invariance of the integral under the change of integration variables. So usually we can write infinite number of differential equations denoted by ln. They are called Virasoro constraints because they satisfy the Virasoro algebra. So sometimes they start with -1, sometimes they may start with 0. There may be some other modifications, but this is the general case. Next is the so-called integrability, which basically means that the partition function also satisfies some bilinear equations. So these are linear operators, and the partition function also satisfies some quadratic relations, also differential. Or in other words, this formal generating function is a tau function of the product hierarchy, or maybe of some reductions like KP hierarchy, BKP hierarchy, KDV, and so on. So this is rather standard. A new thing, in some sense new thing, is the so-called superintegrability. I will explain it in some detail just now, but it can be symbolically written as follows, that averages of characters in matrix models are given by characters again. So sometimes this characters means exactly means, so characters of some group. Sometimes these are deformations of characters, and maybe the group for which they are supposed to be characters is not known yet. And finally, the double representation, again schematically, is the following representation of the partition function. When we have some exponential of an operator w, which acts on some simple, this object is the one that we want, and we have some rather simple operator w, which acts also on something very simple, usually on identity. So this operator is explicitly realized in terms of these pk variables, and so just formally taking expanding this exponential generates the whole series. So I'll give.
What do you mean by character?
Yeah, I will give an example. Maybe it will be better understood. So it is schematic here. So let's just start with the example of the Gaussian matrix model. So we define averages as averages with this Gaussian matrix measure. The whole partition function with these parameters included just has the same form as before, but with the specific Gaussian potential. I omit normalizations. I suppose that normalizations are included in this integration measure. So it satisfies Virasoro constraints, and here we can write them down explicitly. So these are differential equations in these pk variables. And since we look for, we understand this integral as a formal series in this pk, we can look for formal series solution of this equation. So expand this in pk, and then just solve linear equations for the coefficients. And in this case of the Gaussian matrix model, one can see that this solution is unique. So this set of differential equations, in some sense, completely reduces the matrix model, the partition function of the matrix model. So so integrability in this case would be the following. The matrix model enjoys a determinant representation. So one can represent this partition function as a determinant of a matrix which depends only on I plus j, where these mi's are just sort of moments of this distribution. So I wrote here mu of x, meaning that actually it doesn't have to be the Gaussian measure for this to be for this to be true. The only concern is about integration contours, but I will not go into this detail. Let's just suppose that instead of mu I can write, say, the Gaussian exponential, or multiply this exponential by any polynomial.
You mean Gaussian because the dependence on P you consider as formal series? Or?
Yes, yes. So as usual,
but generally this sort of statement does not depend on anything.
Yeah, it is rather general, but when you want to make general statements, you need to describe some details and peculiarities which may arise, and I don't want to do that. So anyhow, yes. So this representation means that guarantees that the partition function is a tau function of the Toda chain. So and yeah, so as I said, the next property is the superintegrability. So what do we mean by this? So in general, if you want to consider this Gaussian matrix model, you have to compute some averages of invariant polynomials. You can do it in several ways. You can just use explicitly Wick's theorem. So you have a Gaussian measure. You can compute correlators by Wick's theorem. You can also solve this Virasoro constraints order by order. And since this Virasoro so it determines the formal series, and the formal series is a generating function for correlators, and you can find correlators in that way. But nevertheless, you will not find, so it will be complicated to find a general formula. So for a given, so for a generic invariant polynomial. So as usual, the question boils down to finding an appropriate basis in the space of these observables, so invariant polynomials. It appears that there is such a basis for which there is an explicit formula. So, and it is given by Schur functions. So if you take averages of Schur functions of traces of this matrix X, which you integrate over, the answer will be again represented as Schur functions, but evaluated at special points. So what do we mean by evaluated special points? So here's an example of a Schur function that corresponds to partition 2, right? So two boxes, horizontal boxes, right? So it is a function of these time variables, or in terms of symmetric functions, these are just power sums. So it's a function of power sums, and the power sums themselves are expressed in terms of eigenvalues of this matrix. So in terms of these eigenvalues, these are all symmetric functions, but we want to look at Schur functions as functions of these power sums. So then we can put these power sums equal to something. So for example, Schur of n means that we put all power sums equal to n and get n over 2 plus n squared over 2. So Schur function of delta k1 means that we leave only the first. So we put only the first power sum equal to 1, else to 0, so it will be 1/2 here, and the same here. So in this case, it will again give 1/2. So this formula is just Schur functions taken at specific values of their variables. And furthermore, one can even notice that this ratio of Schur functions evaluated at these points has actually a nice factorizable form. So this, of course, can be stated in different terms. So, for example, in this specific case, this formula works for Schur functions. So Schur functions are just literally characters of the GLN in representation R, and of course
for reducible representation.
For reducible representation.
For reducible, it doesn't work.
Well, for this for decomposable, you will have a sum.
Just the main non-triviality is that your left-hand side is linear, in Schur, while right-hand side is non-linear. That's why you cannot.
Yeah, of course. Well, it wouldn't work if we take sum of representations, and it wouldn't work it wouldn't give a sum here. Yes, but it just works. So R means Young diagrams. So R is parameterized by Young diagrams. So these are reducible representations. Yeah, and of course, all these quantities can be. So all these quantities mean something in representation theory. So Schur of n is actually the dimension of this representation of GLN, and Schur of delta k1 is the dimension of the corresponding representation of the symmetric group. So the diagram R also parameterizes representation of symmetric group, and this denominator is the dimension.
I should have asked Sasha, we asked him already, but why do you call this by such misleading term?
Well,
because it's totally misleading. There's no integrability here, moreover, this terminology is commonly known for something absolutely else.
Yeah,
so like for Kepler model.
Well, so first of all, one had to come up with some name, but I'll actually try to explain.
So there is some analogy.
So there is some analogy. It's not direct, and of course it's sort of it's still by analogy, but actually, so part of what we're trying to do here is to push this analogy, or to see if this analogy pushes as far as possible. Let's say. Yeah. So this is no, this is not yet this slide, but. Anyway, so one could think that this property is just a coincidence for the Gaussian matrix model. Well, Gaussian integrals have many beautiful properties, and it wouldn't be that of a statement if it only worked in this case. But it appears that there are many models with different potential and with deformations that have this property. So you can go to non-Gaussian models. So for higher monomial models, Sasha, I guess, talked about it. You could do logarithmic potentials, you could do potentials with external matrix, and you can have sort of non-matrix deformations of the measure, such as the beta or QT deformation. So let me just immediately give an example, and also use this opportunity to introduce the beta deformation. So recall that after you integrate over angular variables, so our matrix integral only depends on traces, so we can integrate out angular variables and obtain an integral or only over the eigenvalues of the initial matrix, Hermitian matrix. So it will look as follows. Oh, sorry, I forgot to include the pKs here, but I hope it's yeah. So you should include sums of xi to the k with coefficients pk that would correspond to the traces in the first formula. So the beta deformation, yes, and after integration you have the Jacobian, which is the van der Monde determinant squared. So beta deformation amounts to, at least technically, amounts to putting an arbitrary power here. So there are various motivations for introducing this deformation, and we will see even further that it's natural in even in some other sense. But from the point of view of matrix model, one could think, for example, about the fact that if we start with a symmetric matrix or symplectic matrix, we would get van der Monde determinant to the power 1 or to the power 4. So it's sort of natural to study interpolations. Anyhow, so we can consider the following case. So we take, first of all, we take the beta deformation, and also we choose a potential of a rather different form from the Gaussian. So if you exponentiate this polynomials, you will get a logarithm. So it's a logarithmic potential with the coefficients u and v standing in front of the logarithm. And it still appears that you can cook up a formula which is similar to the one before, but instead of Schur functions, you should use an appropriate deformation, the so-called Jack polynomials, which will appear anywhere where you input beta deformation. So these are also symmetric functions in x variables, or in terms of, or they can be expressed in terms of time variables, power sums.
In this formula, your Jack depends on each eigenvalue. Yeah, so
yeah.
There you should take off the van der Monde to the power 2 beta, and the rest is the product of the eigenvalues.
Yeah. So it is written probably not in the best possible way. So you take out the van der Monde
in the wrong way, because you change the power of van der Monde. You're right.
You should. I should probably rearrange terms in this expression. Yeah, and the Jack polynomial is the symmetric function of the xi of these integration variables. And again, the answer. Well, Jack polynomials depend on the beta parameter. They are symmetric functions, deformations of Schur functions, which also depends on the parameter beta. When you put beta equal to 1, they reduce to Schur polynomial. I can just maybe write an example. The only one that I remember by heart. So if Schur polynomial of partition 2 is p2 over 2 plus p1 squared over 2, then the Jack polynomial of partition 2 is something like 1 over beta plus 1. And here, actually, I don't completely remember. Maybe maybe I should interchange these ones. But anyway, so you see that at beta equal to 1, all these coefficients reduce to 1/2, and the polynomial reduces to the Schur function. Yeah, so magically, so these are called Selberg or Cadell integrals. So if you write them in this form, you see that this is a phenomenon of the same kind. And where the only thing is that I had to substitute Schur functions with Jack polynomial. Now, as I said, for Jack polynomials, it's not known whether they are characters of some group in the same form as Schur polynomials are. So that's why I said the formula was symbolic. So there are two sort of motivations for naming this phenomenon superintegrability. So first is that it looks like the model is somewhat solvable. So you have your correlators and they are hard to compute, but then if you compute the right thing, you will have an exact example. On the other hand, if you study this, you can actually show that the origin of this phenomenon is an interplay between Virasoro constraints, which are analog of equations of motion, and Hirota-like equations, which, the total or KP equations for the partition function, which is analog of conservation laws. So we have a phenomenon which is sort of similar to superintegrability in the usual sense. To stretch the analogy even further, it would be even better if we found some additional symmetries. So in addition to usual integrability of matrix model, which is the KP here, Doda, if we find some additional symmetries that somehow underlie this problem or phenomenon, this analogy would be even better. And so this is in part what we're trying to do. So anyway, so you're free to disagree with the naming, but
there is another definition of the superintegrability, which is a non-commutative integrability. And the question is, could this property be categorified?
You mean this?
Yes. The equation of the characters could be an isomorphism of some representations.
That's actually a good question. So I didn't really think about it, so I don't really have anything smart to say.
It resembles much to the superintegrability.
Yeah. Yeah, that's probably a good way to, maybe if indeed it could be realized, that would be a good way to think about it. Okay, so finally, what is this W representation? So we can derive it directly from Virasoro constraints. So in the Gaussian matrix model, we can sum up the Virasoro equations. Of course, this sum also annihilates the partition function. And it appears that if we sum them up in the right way, the equation has the following form, where this is this sort of a generalized earlier operator for these pk variables. So each pk variable has a gradient k. And this operator w minus 2 is an operator of gradient 2. And for additional confusion, it's named minus 2. But anyhow, it immediately means that this equation can be solved in this form, at least like formally in terms of operators. And you can verify that if you expand this exponent and act with this operator on identity, you will get the same series. And I will present this operator maybe 2 slides later. So it's an explicit operator, somewhat lengthy, but still not extremely complicated. Actually, such representations are also known for just tau functions of integrable hierarchies. So, and we will approach the statement in another form later, but it is known that if you take this W1 plus infinity algebra to a generic element of this algebra, one can construct a tau function of an integrable hierarchy by by the same formula, where instead of this W minus 2, we will put the corresponding operator. So now, an interesting fact is that these two phenomena, they interplay in a nice way. So for this we need one technical step we can take this generating exponent under the integral and expand it into characters. This is the famous Cauchy formula in the theory of symmetric functions. And then the partition function of the model, I'm still talking about the Gaussian model, is going to expand into averages of Schur functions. So in front of each Schur function of pk, we'll have an average of Schur function. If we substitute this expression from before, we'll get this explicit formula series. So can we derive this explicitly from Virasoro constraints, which are equations for this series? And yes, we can, and the answer is provided exactly by this W representation. So as you said, you obtain this exponential form, and this W minus 2 operator is just the following explicit operator, and you can see you can indeed act on identity of this operator, and you won't get 0 because there is a differential part, and there is a part which multiplies by p1 squared and say p2. And the key observation is that this W operator acts nicely on Schur functions. So it has a representation in the space of Schur functions, where it's a degree 2, so it adds 2 boxes to the corresponding partitions. So if this was partitions with number of boxes, partitions here, so this again expands into Schur functions, and partitions here will have 2 boxes more, and we see this coefficient appears in front. This coefficient is exactly a product of this factor, so one can. So this is also called the content of the corresponding box of the Young diagram. So this factor is multiplied exactly over all the added boxes. So we have 2 boxes, and so there's going to be a quadratic expression here, and this coefficient is exactly the coefficient that appears in a way more simpler formula. Just in how the multiplication of p2 times the Schur function expands into Schur function again. So since Schur functions are bases, such expressions, of course, should expand into Schur functions again, and this coefficient is exactly what appears here. So we see that this operator acts very similar to this p2. So after we notice this, we can just do a simple technical exercise. We take this operator to the power n, acting on identity. We represent the identity as an empty Young diagram, and so each operator adds, each time the operator acts, it adds 2 boxes in every possible way, and in this way we obtain. If we act with power n of this operator, we obtain a sum of all partitions with 2 n boxes. While this coefficient actually can be computed by noticing that this is a coefficient with which p2 to the power n acts on 1. Well, it's the same as p2 to the power n itself, just formally written here. And they can be just deduced from expanding this exponential in 2 ways, as an exponential and as the Cauchy formula, and using the Cauchy formula. So identifying this coefficient here with this coefficient here, we finally will obtain this superintegrability formula. Or this explicit formula for character averages. So it actually appears to be one of the most efficient way of proving this formula. Well, in the case of the Gaussian matrix model, you can do it by just using Wick's theorem in a clever way, but still it seems to be like the most effective way, which also has some underlying algebraic structures, which seem to be responsible for this phenomenon of nice factorizable formulas. So after studying a few other examples of other models, it's clear that one should just study the whole algebra of operators that have this nice action on Schur functions, and this algebra of operators is exactly this W1 plus infinity algebra. Before even introducing formally the definition of the algebra, let's start again with an explicit construction. So take this operator W0, which is now homogeneous, so you see the degrees here add up, which it is also known as the cut and join operator, corresponding to this Young diagram. And it is the operator for which the Schur functions are eigenfunctions. And well, the eigenvalue is again the sum of contents. Now, if you take this operator and denote by E0 just P1, you can construct explicitly using iterating commutators first a series of EM operators and then commuting EM operators between themselves, construct the operators HMK. So M is the number of commutators with W0, and K is the number of commutators between EM and EM plus 1. So just to list some examples, so here are E1 and E2. So you can, this is a simple calculation. You can write explicit form of these operators. So the first claim is the operators constructed in such way they commute. So for a fixed M, operators with K1 and K2 commute with each other. It's actually, so it's actually non-trivial to show this from the iterative definition. So it's, I will later comment on it, but anyhow, one can check this. And then the second claim is that their action on characters is exactly this nice formulas that we seen before. So this is, there is misprint here. One should also, yeah. So this SQ. Oh. Okay, I should do some magic now. Yes, this SQ should be here. So we can construct operators which act similar to multiplication by pk, and also have a rather generic, so any power of this content thing as a coefficient. So in particular, the W minus 2, which we studied for the Gaussian model, is exactly the H21 operator. So it acts with coefficients similar to P2 and has this factor to the power 1.
Sorry, this W0, what's the relation of this H and K with W0?
So, well, W0,
yeah.
Well, they are constructed using W0. So you construct EM as an iterated commutator of P1. E0 is just P1. So you explicitly commute this M times.
No, maybe it's better to draw a picture. I don't know if you have it in the slides.
No, I don't. Anyway. Well, yeah. So you can actually draw this in a picture, and this will remind the structure.
But these W's in your cases, they're all modes of d5 cube or something like that, or what?
Which,
no, you had before W minus 2, which was also cubic, right?
Yes.
And this is cubic, so
yeah,
it's something like cubic power
close to that. Well, so I will later give like explicitly the formula how you construct. This is a representation of this W1 plus infinity algebra. But even here you can start drawing the picture, and you can start reconstructing this algebra. So if you have the operator is 0, and you can draw this picture where say this will be the number of pk's, so which is also known as the spin, and this will be this degree. So
in this language, both W0 and W minus 2 lie on the same horizontal line.
Yeah. So
and
if you
have the same number of keys.
So if you have pk, if you assign to pk each pk degree k, then say, well, let's do k. Yeah. So this will be E0 equal to E1. Then somewhere here you will have the operator L0, which is the Virasoro part, and here you can draw the operator W0. So acting by W0, you increase, you can check that you increase this number of pk's by 1. So acting by 1, you will start to construct a tower of operators here.
On this, what is this line for? On this line, so on vertical line, you have kind of 0 modes of W1 plus infinity.
Well, these are modes of degree 0, yeah. So and of different spin. Yeah, if you want to fix a spin, so then it will be the horizontal lines. So the Virasoro algebra will lie on this line, the W3 will lie on this line, and so on.
So each WK algebra will have always a degree 0 operator. That is the
when you commute with W0, it increases the spin but doesn't change the degree. So if you start with degree 1, you get this E1, which is W0 times E1, commuting with E1. So you will get operator of degree 1 and spin 2. So you start with spin, so this axis starts with 1, this is 2, this is 3. So this is on spin 3 but degree 0. And you construct a tower of operators which are, so first you construct a tower of operators which are of degree 1 but of spin, but arbitrary spin. Yeah. And then you start commuting them between each other. So if you say on this picture, color would be helpful. Anyway, so in this picture, E2, iterative commutators with E2, so you can write it as the adjoint action of E2, can be depicted by this line. Why? So because it is of spin 3 and commuting, it means that after commutation you will raise the spin of your operator by 1, and instead of degree 1 meaning that you will raise the degree of your operator again by 1. So, for example, if we take the case m equals 1, then we need to compute, act adjointly by E2 on the 1 multiple times. So we will get in this picture just this line of that goes with the angle 45 degrees.
But altogether, this is W1 plus infinity.
Yeah. So that's what.
Why do we need so strange representation?
No. So see.
For something well known.
No. See I was just about to say that this is exactly the W1 plus infinity algebra, but now what I did is I explicitly constructed by explicit iterative commutative formulas operators with a specific property with the action with such action of these operators on Schur functions. So this is a sort of explicit description of some particular commutative subalgebra or subalgebras in the W1 plus infinity algebra.
And what about this commutative subalgebra? Is it maximal or probably not maximal? What can you say about it? Why
in what sense maximal?
I don't know. But
there are many. So for each m, we obtain a commutative subalgebra. For each
so
m.
It is for the same m only. Yeah.
Yeah. So there is the standard commutative subalgebra here of degree 0 operators, but it appears that you have a bunch of lines which correspond to more commutative subalgebras.
And this one which is on the vertical, it's diagonal inference.
Yes.
And those are not.
Not.
The rest are not.
Yes. So also I'm following a bottom-up approach. So I could just start with stating that this is the W1 plus infinity algebra and describe some commutative subalgebras. But I want to just describe how this appears when you study this property of matrix models. Yeah, so using these operators you can generate the following partition functions, which one can recognize it is a subset of hypergeometric tower functions. And so we can we can also speculate that these commutative operators are exactly some of these additional symmetries responsible for this superintegrability. So we have the usual Toda-like integrability for such partition functions, but also we see that there's an additional commutative structure here.
So for each fixed m,
yes,
since you have a commutative algebra, can we consider the common eigenvectors of this HKN?
Yes. So actually, I don't have an explicit formula here. It is a little technical, but you can construct eigenfunctions of these operators. At least, so now these operators are realized in these pk variables, right? So this is specific representation. So you can construct eigenfunctions just immediately from this function itself. So after certain conjugations, this function itself will produce eigenfunctions for these operators, common eigenfunctions.
So you're getting the tau function of Toda lattice, yeah?
Yes.
Two sets of p's, p and p
bar.
Yeah. So there is this n is 0 time, right?
Yeah.
And what is m?
Well, these are just different tau functions.
Yeah, some parameter of solution probably. Yeah, but it cannot be somehow defined in any other in any other term.
Well, yeah, I mean, so actually, so in some sense you can say that we have, so there are two ways probably to describe tau functions, right? So you can state, you can present the elements of the Grassmannian that corresponds to the tau function, or you can explicitly present the element of W1 plus infinity that corresponds to this tau function. Actually, what we're doing here is that, in some sense, is that we explicitly describe, so for this class of tau functions, what is the corresponding element of W1 plus infinity.
And about the element of Grassmannian, nothing. About the element of Grassmannian, nothing is known.
Well, something
or some peculiar property.
Yeah, I don't know. The simple answer is I don't know. Well, maybe you can distinguish such functions among other hypergeometric tau functions, but
so since it acts nicely on the basis of shoes, this suggests that probably interacting on the Ferdinand, the answer is nice, but it doesn't.
Yeah, but so what? Yeah, so just now finally, so we just see as I described, you see that this algebra is exactly this W1 plus infinity algebra. So a short, at least formal definition would be that there's a central extension of the algebra of differential operators on the circle. This combination is z to the m, d to the m, where d is this dilatation operator. Well, you can also, of course, use a basis of just d over dz, but this basis is usually simpler in commutation relations. So, and then the operators of this W1 plus infinity are exactly this Wn of, so for each polynomial in D, you have operators W of this polynomial, Wn, this polynomial, and they commute. So their commutation relations are exactly as these differential equations, differential operators plus a central extension. Yeah, and so all the formulas that I showed before are nothing but bosonic representation, well, a single boson representation of this algebra, and you can explicitly obtain it via an explicit second quantization formula. So you take a scalar field, you have its modes, and you identify these modes with Pn and d over dp. Now, again, in terms of this algebra, it appears that these operators, the commutative subalgebras, are actually really simple. So we started from something complicated, but we find that in this algebra, it's actually a really simple family of operators. This one body representation, by this one body representation, I call exactly this operators on the circle. So these are just powers of a given operator, and powers of a given operator, of course, commute. Just simple as that. And but the only thing you need is to identify the pre-images. So since we started with working with a particular representation, we need to identify that this is indeed the pre-image.
Excuse me.
Yes.
How this algebra is related with the Virasoro algebra?
The Virasoro is just one subalgebra. So here, this is a picture of this is a vectorial description of this algebra. You have a bunch of points. Each point corresponds to an operator which corresponds to, so z, the power of z is this degree, and the power of the highest power of d in this polynomial is this spin. So this algebra vectorially is depicted here, and you have
as the universal enveloping algebra or something like this.
Well, it's not. What's the question?
Could W1 plus infinity algebra be interpreted as a universal enveloping algebra for the Virasoro Lie algebra?
Well, it is rather a sub-algebra of the. So you could say that if you take
for U1 hat, rather.
Yeah, if you
can be constructed as polynomials of the current.
Yes.
Yeah, but this is still a sub-algebra of this U1 hat. The universal enveloping algebra of U1 hat is bigger than this W1 plus infinity. So the Virasoro is this particular line here.
That's okay.
Yeah.
And if you even can universal enveloping.
Yeah.
But here we are considering only operators. So
well, the statement that you can take U1 hat this will be generic operators made from pKs. So say, for example, in this representation, you have generic operators made from this and this. Yes? But this algebra is smaller than these operators, than the algebra of the whole, so while algebra of this operator.
No, that is
yeah. So yeah, and so you can do this iterative construction in this one body representation as well, and indeed I identify that these operators are images of this family. Yeah, and using this, so this iterative description is also useful when you try to, for practical reasons, when you try to actually compute these HKM operators in terms of these time variables. If you want to explicitly realize this differential operator, this so you should combine this second quantization, the knowledge of these preimages, and this iterative construction. And then you can rather efficiently compute and explicitly and efficiently compute these operators. So if you have a bunch of commuting operators, it's tempting to construct some integrable systems corresponding to these commuting operators. And in these terms, what you should do is just rewrite all of these operators. So from power sums, go to the eigenvalue variables, right? So it is actually well known that, so one well-known fact is that the vertical line here corresponds to the, after this transformation, will correspond to the trigonometric algebra, quantum trigonometric algebra system. But interestingly enough, so we have more Hamiltonians. So we have more commuting subalgebras. And in fact, so you can do this computation and demonstrate that, for example, the M equals 1 family corresponds to the rational algebra. And the other families are actually some new, well, at least unknown to me or my co-authors or any literature that we studied, new integrable systems. Yeah, but unfortunately, we have to do one step, because the systems turn out to be eventually effectively free, or if maybe not free, but sometimes they are just decoupled. Well, they are many body systems, but they are decoupled systems of non-interactive particles. But what happens is that this non-trivial coupling appears after the beta deformation. So we need one more step. So I have already described how the beta deformation works on the level of matrix models. So you introduce beta in the van der Monte determinant. But it actually also works rather simple on the level of these operators and on the level of this iterative construction. So you take, instead of W0, you take this beta deformed analog. So you see it looks completely very similar, but there appear some beta dependent factors, and if you put beta equal to 1, you return to the previous case. Then you just do the same, construct these operators, construct these Hamiltonians, and again, the statement is that these Hamiltonians commute for fixed M. Now, these Hamiltonians also should act nicely on some functions, and these functions are, of course, Jack polynomials, and you have this deformed formula, and this is for a specific representative, h to 1 beta. It is the operator relevant actually for the Gaussian Hermitian, for the beta deformed Gaussian Hermitian matrix model. And using this operator and the technique that I described before, you can actually prove the superintegrability property for the beta deformed Gaussian matrix model. So I presented previously a formula for the logarithmic model, but in the beta deformation of the Gaussian model, you also have a similar formula. And actually, it is, well, it wasn't clear how to prove it. So
this is the only way.
Yeah, this is the only way we know to prove this formula in this model. So otherwise, it was an experimental fact. Yeah. So now we can talk about non-trivial integrable systems. I will not go into great detail, but so what you do is you go to eigenvalues. So for example, for the m equals 1 family, you get exactly the coalgebra. family of closure operators. So these i's are just nothing but Dunkel operators, and you can calculate that h or k1 are just well. This sign means that you should do some conjugations as well, but I didn't want to overload the notation. So these are basically, after some simple transformation, closure systems. So for example, h21 is just this operator. Now, interestingly enough, you have a family for m equals 2. And you can just explicitly construct what are these many-body operators. And you see, so you can see that its first interesting feature is that the family of Hamiltonians starts from the quadratic operator in momentum. So here, this true Hamiltonians of the second order operator is the second conservation law. The first one is moment, sum of moment. Here, the first conservation law is already quadratic, and after a simple change of variable from lambda to mu I squared, you can see that it is actually similar to the closure system itself, but it looks like a system of particles with closure-like interaction, but each particle also moves in inverse square potential. So as I said, if you put beta equal to 1, it is not a free system, but it's decoupled, so each particle decouples. And also for comparison, as I said, this W0 beta operator, so this is the trigonometric closure if you do the exponential, if you make an exponential change of variables. So, and you can study this for higher m, and well, these are some, maybe these are some trivial systems, trivially, somehow they may be trivial, somehow they can trivially be constructed from the closure system, we don't know, but just you can look explicitly and you can see that these are some explicit many-body systems, and you have an infinite number of commuting operators, so you can suppose that it's integrable. Okay, so we have seen that these commutative subalgebras in this W1 plus infinity algebra are probably in some sense responsible for this matrix model superintegrability, or at least the structure appears anyway. So after beta deformation, they correspond to non-trivial integrable systems. And actually after this beta deformation, the algebra also gets deformed. So the operators already do not commute as W1 plus infinity. And the final question to ask, so at the level of abstract algebra is this commutativity a feature of representation? So we worked mostly in specific bosonic representation. So it might be that this commutativity is just additional relations that appear in this representation. So can we prove this using some definition of this algebra as a set of generators and relations between these generators? So the relevant algebra for the beta deformed case is actually this fine Yangian. So there are many ways to define it. I will use one that is probably the most practically applicable to our case. So it is an algebra with a set of generators psi f, e, I, with a set of simple commutation relations and a set of complicated commutation relations. So first there is a set of quadratic relations which involve two parameters sigma 3 and sigma 2. So there is actually a third parameter sigma 1, but they are related, so there are two independent parameters. There are a bunch of such relations between E and E, between E and psi, and between F and E. And there are also cubic relations which there are, well, you should probably write Serre-like relations, so they resemble Serre relations.
All of them are finite.
What do you mean?
Every relation involves finitely many terms.
Yes, yes. Yeah, so these just look exactly the same, but with some interchange. And so the affine Yangian is actually a two-parametric family of algebras. So you have sigma 3 and sigma 2, and the beta deformation corresponds to some one-dimensional sort of subspace. So you put sigma 2 and sigma 1 equal to this related to beta in the following way. And actually, when you put beta equal to 1, so this goes to 0, this goes to -1, and the algebra actually reduces to the W1 plus infinity. So here you have in the commutation relation some non-Lie algebraic terms. So this is not expressed via Lie bracket. So this is not a Lie algebra because this is a Young. So when you put beta equal to 1, it reduces to the Lie algebra, which is this W1 plus infinity. So when you can do an exercise which is technical, but still you can just cook up a proof by induction, sort of, that such constructed subalgebra of this Yangian is commutative. And so you only use generators and relations, and what is it? So it is not a feature of representations. So also interestingly enough, the proof only uses these set relations, which actually do not depend on these parameters. So it means that we can sort of generalize. So it's not only for this beta deformed case, but it's just generally for this Yangian. And well, to our best knowledge, there wasn't really any. Well, so we think that it is a new result. So that these are some new subalgebras in this Yangian, but probably the guess is that they are actually related to something so on a higher level. So if you take this quantum toroidal algebra with two parameters Q and T, then it is known that there are families of Heisenberg subalgebras there related by Salto-Z transformations. And we suppose that these subalgebras here are just so the generation of these Heisenberg subalgebras, and it's only it's only half of this Heisenberg subalgebra, so say only the positive part. And so you can also do the same for everything for this F counterparts. So you can put F here, then this generators should be called H minus Km. But everything works exactly the same. So okay, so I'm probably supposed to finish. Yes. So let me just repeat once again. So the superintegrability of matrix models. So if you work up bottom up, you finally arrive to commutative subalgebras in this Yangian algebra. And what is nice is that you can have an explicit description of this algebra in terms of iterative commutators. You can immediately construct their representations. So the representation of this algebra, bosonic representation in the space of the symmetric functions, so Schur or Jack functions. They have nice explicit action. So yeah, you can construct integrable systems by going to this eigenvalue representation, and in such a way you supposedly construct some new integrable systems. And so another comment is that I have omitted this part related to F generators. So even here I drew on half the picture, but you can do the same using this F M generators. So for this you would start with F0 equal to D over dp1 and construct similar family of operators, which now is not raising the degree but lowering the degree of the Schur function. And in such a way, nearly everything is the same, except for if you want to construct W representation from these operators. It appears that since these operators are now, instead of looking as, say, P1, they look as, they actually act similar to D over dP1. It means that you cannot construct a W representation, so in the form, say, you cannot take the simplest case and construct the following W representation, because this is E over D, E to the D over dP1, so it's trivial. Instead, it happens so that you have to act again on exponent. So this acts on P. So you take some pk parameters, you take some additional jk parameters, and after this, you will actually also obtain tau functions, but they will now be so-called skew hypergeometric tau functions, which involve skew Schur polynomials. But you can describe them explicitly as well, so but I didn't talk about today. And so there are various future directions probably that could be formulated here. So in particular with relation to this Yangian is this interesting family of commuting operators, which I also omitted. So in terms of the W1 plus infinity algebra in one body form, you can also construct operators of such form. So before Q was equal to 1, so now you can generalize. Again, the commutativity is obvious. And you can construct the corresponding bosonic representation, tau functions, and so on. Everything works. But now, what is interesting is that somehow it is unclear how to lift this to the Yangian. So there should be more commutative subalgebras in this Yangian, and so more than trivial integrable systems.
So beta equal 1, they correspond to the lower, how to say, octant of on this picture, and they stop to compute at beta not equal to 1.
Yeah, so for some reason, so these are operators. So before we had operators starting from E1, E2, and so on, and this could be organized in rays that go upwards, and so these new families are going to be rays that go something like this in different language. Anyway, so for some reason their commutativity is broken when you introduce the deformation. So but this is probably so a feature of us lacking some.
So it's unclear. Either we don't understand something and don't see some possibility that would allow to make them commutative somehow, or it is indeed a no-go.
So I believe this is our lack of skill. That so we need to. So it seems like this uplift is just not that naive. But anyhow, the prediction is that there are even more commutative subalgebras in this Yangian. And also it is interesting to return backwards. So we start with some examples of matrix models and build it upwards and constructed very general partition functions with very general W operators. And so the question is whether you can return and cook up matrix model representations for all of these cases. And so in fact, it appears that so in some cases you can, so possible representative were constructed, so for example in this paper, which correspond to this k bigger than 0, so this is exactly the family that I was describing. So for pretty much for generic M, you can construct some multi-matrix model, but it will be rather complicated. So it's a rather technical construction, and maybe there should be some easier, transparent so matrix integrals which correspond to these models. And for the negative branch, which I did not discuss today, but so which correspond to the skew tau functions, they are also called WLZZ matrix models due to these people, and so due to some our work. So you can also construct models for these cases. They now begin to involve some external matrices, additional external matrices. But anyhow, it's this piece is still not completely clear. Okay, I think that's about that. Thank you so much.
Any questions?
I have a question, maybe it's silly. You constructed, you said that this beta deformation gives you the one of the families, I think m equals to 1, was the trigonometric algebra family.
So the rational algebra.
Rational algebra. And you say trigonometric was related to what?
So on this picture, so this picture corresponds to beta equals to 1, but if you take this picture and then beta deform it, then this family of operators in this algebra and that have 0 degree but different spin, they would correspond to the trigonometric. So it's trigonometric algebra. Now this family, so this commuting subalgebra, again after beta deformation, will correspond to rational algebra. And so actually, it happens that the one that is the mirror sort of family for F operators also gives this rational closure, but it's the Hamiltonians are conjugated. So the other families give some other operators.
So my question is, you write down these Hamiltonians in terms of these variables, collective variable speed and the derivative speed, but there is a way to write down them in terms of some field phi, which is some bosonic field, and in this case, for example, trigonometric closure becomes the model which is related to some integrable equation, which is known as Benjamin equation. So didn't you try to write down this representation in terms of field is somehow similar to the representation you showed in the undeformed case when you had these V generators in terms of the fields, E with the phi, exponent of phi. So how do you write these Hamiltonians that you found new integral systems in this way as some field equations?
That's an interesting question. So I don't know the answer. What you can do is to write these operators in terms of just bosonic fields. I basically explained how to do it. Yeah, but so what is their interpretation as field equations? We don't know.
So the question is whether you will find some new field equations which are integrable.
Yeah, maybe yes, but so.
Okay.
I hope so.
This beta deformation, where can we see from matrix model? So how to insert this beta to matrix model?
Yeah, so in matrix model, beta deformation corresponds to changing the power of this van der Monde determinant. So maybe your question is whether you can see it in terms of a matrix integral, right? So what you do is you take, say for the Gaussian model, you take this, say, Gaussian integral, then you integrate over, so you diagonalize, right, your matrix, and you integrate over the U's, and then you have, so let us write this in a better way. So then you have van der Monde determinant squared. So you have something, say f of trace x to the k, then you have your f of xi's into the sum xi squared product and dxi, right? So now beta deformation is just to turn on a general power for this van der Monde determinant. So when you take an integral, so it's usually thought of in the following way. You take integer powers of beta, and then you can do your integral explicitly, right? And then you sort of analytically continue, or so non-integer beta, non-integer divided, so say 1/4, right? So the question is how to choose the quantities of integration here. But what you usually do is you take integer betas and then say that the answer. So the answer depends very simply on beta. So you can just analytically confirm, continue.
But then, if the question is about generic with the LZZ model, then the answer about matrix model representations is not tricky, right?
Yeah. So if you want to now generalize, so as I said, you can cook up. So for example, for this m=1 series, you can write down a two-matrix model. So it's dx dy. Now it's trace xy. So x is going to be Hermitian and y is anti-Hermitian. So for this trace xy to look like ixy. So it's a sort of so like a Fourier exponent. And then you take the following generating function. So you take pk trace x to the k plus p bar k trace y to the k. And now you have a double matrix integral, and it will correspond to generic functions with m=1. But now if you, now beta deformation of this is already unknown.
No.
Well,
It's CMI. So I mean,
we're working on it, but it's unknown.
What do you mean by beta deformation? But here you just will have Vandermonde of x times Vandermonde of y, right? If you count the eigenvalue integral, there will be a single Vandermonde for each
times the angular integral.
Yeah, but
you have so since x and y interact here, you cannot easily integrate the angles.
And this is the complication of the beta case. So what enters is the beta analog of this on the integral.
So you have interaction. You do have an interaction term that has both xi and yj, the eigenvalues of this.
So what? But for this particular integral, you can count eigenvalues, right?
No,
I'm just asking what you call by beta deformation of that.
Exactly. So since you cannot reduce this to eigenvalue because you have your matrices intact.
What's the difference with the top?
Because single.
The top, you count the first eigenvalue integral and then you just put beta there. Yeah.
Yes. This is not invariant under transformations. So this is only invariant under simultaneous transformation.
Yes.
But not under generic. So generic transformations, you would have angular variables for x and for y, and it would mean that you do the transformation here with one matrix and here with the other matrix. And this is not invariant.
Я не понимаю, что вы говорите. Я говорю, что в терминах собственных значений вроде для этого интеграла есть формула. А вы говорите, что ее нет?
Нет, есть. Одна монетарная матрица остается там между. Ну, будет
нельзя же две матрицы организовать.
Да. И, собственно, то, что у нас там написано, это то, что okay, so just define the value of this angular integral to be the normal expansion or the required expansion of the Jack functions. So in this sense, it's like a partial solution of the matrix.
I can explain more detail. I mean, so no, but technically, I think it should be clear. So you have two matrices, and you have to integrate over angular variables of them, and angular variables of those are independent. So if you try to diagonalize, if you take unitary transformation of both these matrices, these unitary transformations are independent. There are two independent unitary matrices, and this exponent here is not invariant in this transformation. So you cannot integrate. Well, you will be left with.
You will integrate something like over the product U1 and U2, yeah, and take this as a solution as a very integral.
Yeah. And then you have to. So to do
you give the two Vandermondes in the denominator.
Yes.
And there are square of which Vandermonde from change of variables in the numerator.
Yeah, but there is also an exponent with xy and xi and xyj. And you need to do a beta deformation of the so some sort of you need to invent some sort of beta deformation for this.
I'm just saying clever thing that you can make beta deformation like on top after you already integrated, not in terms of matrices. Or you may call it normal matrix model or whatever. There is beta deformation, right?
For two matrices.
If there are normal matrices, then for sure it exists.
If one of them is normal or what?
No, but the point is that you have to deform this unitary integral. So if you take a unitary integral before the deformation,
if you start with eigenvalue integral, you don't have any angle integral anymore. I know nothing about that, but I heard that people call by beta deformation here something like that. You just start with an eigenvalue integral with some complex, so there is a point. And then exponent of some function xi, yi plus u of x plus some w of y, yeah? And I thought that people call beta deformation when you put some powers here. That's not correct.
Maybe the short answer is that if you do like that, then you do not obtain the characteristic.
Okay, we can discuss maybe during the coffee break. So there are no further questions. Let's thank our
Ну вот, мы все как бы интегрируемость, мы назвали интеграл как КД. Ну, не, как раз вот в том примере, здесь тот интеграл, он называется интегралом КД. Да, есть такой вот, допустим, когда хватит C3 интеграл. Нет, если тоже есть такое, то тоже просто пример суперинтегрируемости. Есть разные интегралы, которые называются. Но это не то, что мы сейчас обсуждали. Нет, это другое. Ну, это экспоненциально. Когда ты, ну, они логарифмически плаваешь, что... Ну, это как бы неинтересно, да? Нет, почему интересно? В смысле, вы ничего нового не получите. То есть вы получите тоже G1 плюс инфинити. Если какие-то операторы решаются, ну, я не знаю, ну, слушай, я уже все забыл, но у нас тут вот с Ильей написано такая формула. У нас тут написано сейчас. Ну, они реально коммутируют, потому что это мод Гейзенберга. Я не очень понимаю, откуда взялось, что мод Гейзенберга. Вот берем вращаться. Нет, я теперь понял, что значит, хорошо. Если это уже представление, да, тогда не реально Нет, я сейчас, допустим, вот это верно. Тогда эти коммутируют и все. Да, а эти высшие чуваки как через G переписываются. Это, ну, правильно я думаю, моя интуиция такая, что их надо коммутировать, просто поднимая. Не, ну просто вот это такие. То есть у нас есть вот такой диагональный гейзенберг, да? Ну, здесь живет это U, да? J. Здесь как бы живут веросоровские генераторы. Они, конечно, вот так не коммутируют. Да, но типа так, типа веросоровские генераторы, да. Что типа свободных бозонов, это там сумма M минус K и сумма по J, да? Ну, у M это сумма M по J. Ну, конечно, бесконечная сумма, но как каждое представление немножко сделать поворот. Ну, то есть индивидуальные моды всех бозонов, они просто сами все коммутируют. Поэтому, ну, правильно я думаю, что это вот они как бы есть. То есть, как бы, если я вот так вот сейчас все перепишу, то есть я интегрированный систему будет отвечать тому, что у меня есть бесконечное число бозонных полей по полюсам, и вот у них положительные моды в разных рождениях, они все коммутируют. Ну, может быть, это к этому имеет. Ну, просто что, ну, если это к этому не сводится, значит, интегрированная система тоже есть. И она другая. Не, ну это же легко пересчитать, правильно? Нет, ну да, в смысле, надо искать каждый из операторов, он конкретно. Да, вот это с этим просто можно. Да, я имею в виду, ну мы знаем, как генераторы, все, как вот все это выражается, но здесь это поведение, оно такое, в принципе, честно. Нет, давайте мы не знаю, но просто вот эта серия, она же как все содержит этот оператор с разными числами. Версов 2, здесь уже 3, например, у нас коммутирует оператор спина 3 с оператором спина 2. Нет, спина да, но как сказать, сейчас не, ну вообще, я как скажу, значит, если я буду выражать, я могу решать эту задачу, у меня есть толку спина 2, спина 3 и так далее. Я могу пытаться просто по этим формулам выражать через бозон. Каждый раз это будет, как сказать, но это будет там сумма все по числу бозонов, прям правильно? И число пока это решил да. Число бозонов это такая совершенно ограниченная. То есть как раз если я буду коммутировать АК, это не те АК, да, это не те как бы. Это не P и DPTP, это другие. Ну да. Они через те будут выражаться каким-то конструктором. Не, ну это вообще интересно. То есть следующий. Нет, их можно как-то так описать, что вот есть вот эти вот, допустим, бозоны там, да, карты. Да. И вот это вот все семейство можно на самом деле получить как действие некоторого оператора такого сопряжения. Да. И вот этот О можно, в принципе, явно построить из вот этих вот. Вот этот О, он типа Е в степени сумма там, ну,
с каким-то там коэффициентом zn, вот примерно там этих вот. Вот если их набрать, cn, это вот примерно там z степени n.
Это такой вот этот curly O оператор.
Да. Не, ну сейчас я точно не знаю, конечно, но насколько я помню, эта формула там просто задешево следует. В смысле, что они вот так такие, следуют там как-то, если за матрицы. Не, ну смотря с чего. Ну да, за матрицы. Потому что я говорю о том, что давай я один просто коммутатор и соответственно. Да. Ну нет, с коммутатором если ты как бы заранее за матрицы что, это я тебе, собственно, нашел, но пока ничего не буду. Хотел бы, конечно, из матрицы и вот эти семейства. Нет, я могу вспомнить, но получается, что у нас из матрицы вот.
Матрица как другое представление.
Что H0 с H0 коммутирует просто вот выводит из матрицы вводить все.
Нет, H это
Не, вот есть формула. Да, эта формула тут даже не написано, как она двоится, потому что она типа у нас решит, да, стереально. Потому что там такое свойство, ну да, правда, нет.
Сейчас это на вот этой картинке что это тоже?
Это вот нижняя вверх. Нижняя вверх.
Да.
Ну да.
Просто если ты уже с одной стороны знаешь, что это измеряется, а с другой стороны знаешь, что это измеряется.
Нет, я имею в виду, что надо подумать, как бы, да, откровенно говоря, как легко доказать, когда у меня это все представление на произвольном числе центра степени, то, наверное, это можно, мне кажется, я это без представления доказываю.
Нет, ну, в общем, я как бы выше, на самом деле, это не то, что происходящее сон. Просто
я не спорю, хотел бы представить, что это за оператор. Если нормально представить, я помню, как это доказываю, какие-то банальные упражнения.
Ну, я, честно говоря, видел в одной статье некоторую фразу, которая, типа, дальше несложно показать. И вот это несложно показать, мы и пытались показать, поэтому я так.
Да. Ну да, я что-то такого читал. Это наша сколько которая, ну, которая была, ну, не знаю, была на самом деле, конечно, специя. Вторая Москва, ну, вот это уже посложнее, когда там навешиваешь с двух сторон. У нас как бы была задача описать оператор, когда слева и справа там произвольное состояние. Вот это, как бы связано с тем,
дальше уже
Потому что она там почему скачками скачет, это сложно.
Да, сейчас я.
Да, и тут фишка в том, что поскольку из серы и все это устроено так, что можно типа шифтить, грубо говоря, по этому да, если заготовки для дальше сразу значит,
ну, для всех целых, опять же. Ну, с нецелыми какая-то вообще там есть еще, вот видите, еще не говорим, вот, но в чем прикол?
Не.
Да, что вот для гамильтонианов, которые на целых лучах, есть формулы такие явно, что нормальные порядочные. Вот. И это равно 1. А когда не равно 1, там не пишется нормально.
Ну, в смысле, нам показывали,
не, я имею в виду, что вот можно такие мономы, да, БК1, это да, БКМ. Вот. И H это сумма по таким мономам с 2 коэффициентами. При b равно 1. А при b не равно 1. Ну, это, собственно, видно даже в самом двойной оператор. Двойной оператор возникает какая-то ненормальная порядочность. И она начинает везде. Может, не знаю. Да.
Я не приехал 10 минут.
Ну, в целом, как бы считается, что нет просто приготовления
You were going to the platform? Yeah, I just put that for later.
Xavier-Blot, the talk is about the hierarchies of meromorphic differentials.
Thank you. Okay, first I want to thank the organizer for the invitation to be here to do my work. Okay, so almost 10 years ago, Sacha Boyac introduced a class of integrable hierarchies called the double ramification hierarchies. So these hierarchies are constructed using a cycle in MGN bar called the double ramification cycle. And there was many beautiful developments using this construction. And the construction I want to present today is kind of parallel to this construction, meaning that I want to construct a class of integrable hierarchies using another cycle in MGN and bar called the strata of meromorphic differentials. So I have two goals in my talk. Oops. The first one is to present new hierarchies based and this construction, integrable hierarchies. And this construction is based on the strata of differentials, and I will define this later. Of differentials. And okay, so this construction is actually kind of general because it works for all homological field theory. And it works in the classical and quantum setting. So classical and quantum. But for this for the talk of today, I will only make the construction for the classical homological field theory and for the classical in the classical setting and using the trivial homological field theory. Okay, and the second goal of my talk is to study this hierarchy and to give all the results. Okay, so as I said, the main ingredient of this construction is this strata of differentials. So I will begin by defining them. So that's the part one construction. And I will define the strata of differentials. Okay, so I fix G and N, some non-negative integers satisfying the stability condition, 2G minus 2 plus N positive. So this will be the case all the time, and I will not repeat this. But moreover, I introduce M integers, M0, M1, N minus 1. So these are integers. And I impose the condition that the sum of the Mi is equal to 2G minus 2. And now I define a locus in MGN without the bar, so on the modular space of smooth curves, that I denote by HG, M0, M1, N minus 1. So this is the locus of curves, of mapped curves. Oops. So I index in MGN the mark point from 0 to N minus 1. So this is a curve in MGN such that I impose the condition that the canonical line bundle is isomorphic to this twisted trivial bundle. So sum of Mi xi. So I don't know if you all see this condition, but this condition means that there exists on this curve meromorphic or holomorphic differentials with poles and zeros at the xi given by with order given by the Mi. So negative mi give you fall, and positive mi give you 0. So that's the definition of the strata of differential inside MGN. Now I want the definition in MGN bar. So what I do is that I only take the closure. So this is the Zariski closure. Oops. In the moduli space of stable, well, the Deligne-Mulford compactification of the moduli space of A. And this object I will denote it with an overbar. So this is the geometrical ingredient of this construction. One thing is that, as I said, okay, if all the mi's are positive, this is called a strata of holomorphic differential, and if there is one mi negative, this is a strata of meromorphic differential, and this is the case I would be interested in. So, well, if there exists mi negative, we are in the meromorphic case. Morphic. And in that case, the codimension, the complex codimension of this cycle is equal to G. And one remark on this cycle, maybe, well, that's a big difference with the double ramification cycle, is that this cycle is not at all polynomial in the mi's. So, remark, G bar. Not polynomial.
Sure, what does it mean?
What does it mean?
Yeah.
What you could expect is that this cohomology class in MGN is well, it's a polynomial in the mi's such that the coefficient of this polynomial are cohomology class of codimension, well, of the unitude G. I mean, yeah. It is clear?
Well, I think I got it.
Okay. Okay. So now that I define this, I can begin the construction. So first, first I want to introduce to define the Poisson structure.
Sorry, you are going to consider intersection theory for such cycles. So are these at least equidimensional? So you do not need to consider some difficulties with virtual classes or something like that.
No. I mean, this class is only defined like as a closure of this space, so you don't need like a virtual fundamental class to define this space.
So, and if all i's are non-negative, then what's the dimension?
G minus 1.
G minus 1.
Yeah. Okay. So let me define the Poisson structure I want to use. So first, I will define, well, the phase space. So the phase space is not necessary for the construction, but it's, I think, a good motivation for the following definitions. So my phase space P is the set of maps U from the unit circle S1 in C star to C. And questions?
No, so there is some technical problem. Some people who are watching over YouTube, they say that they only see that screen and not that one. Yeah, we'll have to deal with.
Okay.
Yeah, sorry.
Should I continue?
No.
Yeah, continue.
Okay. So this is the phase space I want to consider, the maps from S1 to C. And I don't put any regularity assumption on these maps because this is just a motivation. And what I assume is that each of these maps have Laurent series expansion. So U of X is summed for M belonging to Z of Q M I M X M. And I mean, if you are for the experts of the double ramification hierarchy, well, that's one first difference, because in the DR case, what you consider is free expansions and not Lorentz series.
So sorry, usually people write exponential.
Yeah, exactly. So for the DR case, you have an exponential here.
But here you.
I don't want. Yeah. Okay, so now, okay, what's the space of functions f of p? Well, this is well, power series epsilon, also in P with negative indices, and with coefficient with P with with positive indices. Okay, so that's just a choice so that everything is well defined. That does not matter that much. But what is important is the Poisson bracket. So you can see these variable q's as well an infinite set of coordinates on this phase space. And I want to define the Poisson bracket between these coordinates as QA, QB is equal to I A plus 1 delta A plus B plus 2. So this defines the Poisson bracket on the coordinates. Now how to define this on the functions? So how to define it on every monomial? You use the Leibniz rule. Okay, so now my Poisson structure is defined, and the equation I want to look are of type du over dt is equal to Poisson bracket of u with, well, I have to define what's the Hamiltonian, so this should be an element of f of p. And before defining what's the Hamiltonian, I want to give an example to make everything clear. So let me choose h bar is equal to sum for m1 plus m2 plus m3 is equal to minus 1 of q m1 q m2 q m3 over 3 factorial, and that's it. Other questions? Okay, so now let me compute the equation associated to this Hamiltonian. Du over dt is u, the Poisson bracket of u with h bar.
So sorry, here you have it's also x to some power, but on the
on the right hand side, yeah. Here there is no x, right? Yeah. So I mean, first this on this. So this you should not look at for now. It's for later, okay? Yeah, but I mean, you see, like in this function, there is no x dependency, right? So for now, I'm okay. And actually, like the x will correspond to the Hamiltonian density. And when you remove the x, you go to the Hamiltonians. So let me do this computation. So I want to the bracket of u with h bar, but this bracket is defined with this q variable. So I will use the expression of u in terms of these q variables. So this is sum for m.
So how q is related to p?
How what?
U is related to p.
Yeah, that's what. So I assume that u can always be written as Lorentz series expansion. So q m I x m.
How is p there over there?
So that's the power of m is here. So that's the same thing than for the DR case, but in the DR case you don't have an x here, you have exponential of ix. And that's, yeah.
Yeah, just confuse the tick of p over there, p variables.
Oh, sorry. Yeah, that's q. Sorry. I'm very sorry. Yeah. Okay. So now let me continue to compute this equation. So I use the form of u in terms of this q variable. This is sum of q m h bar I x m. So now I can compute this Poisson bracket using this definition and the Leibniz rule. So this is a very easy exercise. This is given by sum for m1, m2 belonging to z of I m1 plus m2 over 2 q m1 q m2 I m1 plus m2 x m1 plus m2 minus 1. Let me check. Yes, exactly. So this is the definition of u, but you can also derive u with respect to x. So if I derive u with respect to x, I have an m coming here, and then this is I m x m minus 1. And then you can recognize that this expression is actually, you can pack everything in terms of this u variable, and this gives you u of x dx u of x. So this equation is well known. When D spoke about yesterday, this is the Hopf-Freeman equation or the dispersionless KdV equation. So when we choose this Hamiltonian, we get this equation. Very good. So let me now come back to the construction of the hierarchy. So I define the Poisson bracket.
So your Poisson bracket is probably just first Hamiltonian structure of KdV, yeah?
Yeah. So I will make a remark on that. Yeah, exactly. Yeah, it's like shifted, but yes. So now let me define the Hamiltonians. So I fix d bigger than -1, and I want to define so before defining the Hamiltonian, I will define the Hamiltonian density. So Hd, and so since its density depends on x, and this quantity is defined using the intersection number on the strata of differential. So the most important part of this quantity is the intersection number, because it's more or less a genetic series of intersection number, and I want to consider the following intersection number. So you take the following intersection number. So this is a strata of differential. You put a pole of -1, then m1, mn, and 2g minus 1 minus sum of the mi. So as you can see, when you sum all the order, you have 2g minus 2. So that's well defined. Now I put a psi class, psi 0. So the 0 max point is the simple pole. This is this point. And I take the power of d plus 1. And I also insert the class lambda g. So what's this class? This spoke about yesterday, but let me redefine it quickly. So lambda L is the else chain class of the Hodge bundle. Yeah. So the Hodge bundle is a bundle of rank G on the Miller space of NGN bar, and so you take the else chain class. So in that integral, what we consider is we take the top chain class of this Hodge bundle. And using this intersection number, I make a genetic series. So I sum over the genus, the number of Mach points, and the order of the poles and the zeros. So G n such that G plus n is positive, minus I insert also this epsilon, this formal variable which counts the genus. and I insert this formal variable I introduced before. So qm1, qmn of I x sum of mi minus 2g. So each index of this q variable corresponds to the order of a pole or zero of this strata of differential. Okay. So as D remarked, well, this depends on x, and if we want the Hamiltonian of the hierarchy, we have to remove this x dependency. So this is very standard. What I define is HD bar. So this is you should think about that as integration with respect to x. So this is a Laurent series, and so in that case, the integration corresponds to take the residue. So what I actually define is you take the coefficient of ix minus 1 of hd. And now, the most important property of this construction is that hd1 bar, hd2 bar is equal to 0. So this is the integrability condition. Well, okay. So how can we prove such is there questions before? So how can we prove this integrability condition? Well, so I will not give the proof, but just give like a taste of the proof.
So
Yeah.
your Hamiltonians depend on parameters, or not? I mean, you sum up all these n.
All the mi's I sum, the genus and the number of mark points I sum, and that's it. Yeah. So it only depends on x.
No parameters, but if you can do any cohomology field theory.
Exactly. That's so as I said, this construction works. I mean, in that case, it's for the trivial commutative field theory, but it works. I mean, you can insert here any commutative field theory, and the construction works as well. I mean, what you have to do is you have to insert here the commutative field theory, and you have to put new indices corresponding to the index of the commutative field theory, but it works in the same way. So to prove this integrability condition, you have to use a formula of Adrien Sauvaget. And he gave a splitting formula for the intersection of one psi class, let's say psi 0, with this strata of differential. Okay, and what does this formula tells you? Well, what you have on the right hand side of this formula, you have a big sum, but you have two strata of differentials which are glued along the nodes. Of course, you have to sum all the way to split the genus over these two strata and split the number of mark points over these two strata. But the only point, I mean, the point I want to stress is that you have a condition when you glue two strata of differential is that you have a condition on the order of the poles and the zeros. So if A is the order of a pole of one strata of one side of the node, and B is the pole from the other side, what you have is A plus B is equal to minus 2. And that's exactly the condition that we impose for the Poisson bracket. So this is why we chose this Poisson bracket, and this is and once you have this and use the you look at the formula of Sauvaget, you see that this integrability is completely clear.
Does it mean that this formula reduces the computational integrals to the same integrals with smaller values of d?
I mean, yeah. Yes, yeah, I mean, theoretically, yes. Theoretically, yes. And of course, it's a degeneration formula, so you want to compute everything from smaller genuices and with smaller index of d. I mean, but we didn't find any recursive formula to compute this Hamiltonian. So theoretically, yes, but I don't know how. Yeah.
Can you write this Hamiltonians as certain polynomials of u of x and its derivatives?
Yeah, that's the goal of the second part.
I just wonder, does this definition imply that there is at least maybe complicated but still algorithmic way to compute all these integrals to get numbers, or you just consider this?
Yeah, I mean, there should be a way. I mean, and if you look at yeah, of course. I mean, if you have a splitting formula, you can hope to have a recursive way to compute all these integrals. And actually, I mean, somehow the goal to study this kind of integrable hierarchy is to find this kind of nice recursive formula, recursive of even explicit. So another property that we can get directly from this splitting formula. So another problem.
One question is, can you obtain the similar results for different modular space?
Okay, yeah. So okay, that's many remarks I wanted to make later, but that's very good. Okay, one other thing that so that's the construction for the strata of differential. Now, for example, there is a paper of Costantini, Sauvaget, and Schmidt, where they prove the same kind of splitting formula, but for other cycle in MGN bound. For example, you can replace this cycle by the twisted double ramification cycle, which is there's a definition in the of this cycle in the paper of Yanda, Pixton, Konitz, Vonkin. So you look at the Pixton formula for the usual double ramification cycle, and you twist it by inserting kappa classes, and then that defines you the twisted double ramification cycle. And what we did is that we also constructed these hierarchies for this twisted double ramification cycle. Now there is also other formula for any twist. So we constructed this for the first twist, but there exists some splitting formula for any twist, so you can hope to construct this kind of formula. You can also twist this object. There is also the spin version of this object that you can twist. I mean, so there is a lot of work that you can do, but we just did it.
Okay. So essentially, is this equivalent to the splitting axiom of the Sauvaget routine?
Yeah. I mean, as soon as you have a splitting formula, you hope to make an integral hierarchy.
So what is the difference of this integral with the double ramification case?
What's the difference?
Yeah.
Okay, so first, I mean, the main difference is that here, instead of having this cycle, you have the double ramification cycle. And here, instead of x, you would have exponential of ix instead of this x. I mean, no, what are you talking about, the twisted double ramification cycle or the double ramification cycle?
I'm talking about Sasha's construction.
Yeah, okay. So here inside the double ramification cycle, so here what you want here is dr0 a1, sorry, yeah, an and minus some of the ai. Okay. Here it's not x but exponential of ix, and this Q variable, well, they don't have like the, when you take the Poisson bracket, it should not be like the Poisson bracket I defined, but you should have defined it by Q, well, let's say A, QB is equal to I, A, delta L plus B. So there are small differences. But, I mean, the splitting formula for the double ramification cycle is different from the splitting formula for this strata, and that's just like a way to adapt the variables for this strata, this cycle. Okay.
So this Hamiltonians, they are not polynomial in Q.
I mean, yes, they are. That's a property that they are. Yeah. Actually. Yeah. Okay. So before beginning to study these Hamiltonians, I want to give another property. So I mean HD1 minus 1 HD2 bar, this is equal to HD2 minus 1 HD1 bar. So this property is called the tau symmetry. And that means that you can construct tau function using this Hamiltonian. So that's okay. That's the end of the construction. As we mentioned, we can make the same construction for any cohomological field theory. Even more, you can even make the same construction for any cohomological field theory and in the quantum context. So I don't want to go through the quantum construction, but well, there is a standard deformation by quantization approach where you deform this the Poisson bracket in the direction given by the you deform the product between the Q variable in the direction given by the Poisson bracket, and then okay, the key point of this construction is that the Hamiltonian you have here, they do not quantum commute anymore, and what you have to do is to replace this top Chern class of the Hodge bundle by the full class of the Hodge bundle. And in that case, you have quantum Hamiltonian commuting with this target. Okay, but at what time do you have to finish?
30 minutes more.
30 more. Okay. And last thing that we said, okay, we can replace this by the twisted double ramification cycle. Okay. So now that this is defined, let's study this hierarchy, right? Let's okay, so this is the second part of the talk. Well, study and results. And results. And the first property is, well, what you said. This intersection number of, well, let's say minus 1 M1 Mn G minus 1 minus sum of the Mi, psi 0 for any D and lambda G. So this is a polynomial in M1 Mn of degree 2G. So indeed, this cycle is not a polynomial, but once you intersect with these precise classes, you get a polynomial in the MIs. I mean, there are some other classes, of course. When you intersect, you don't get a polynomial anymore. You get a piecewise polynomial. Okay. So now that I have this property, I can I want to look at this Hamiltonian and try to study them. So let's look at well, study of H1. And I already wrote the expression of H1 here. So how to compute these intersection numbers? Well, there are some formulas, but I mean, the easiest way is to, so there's a computer program which was built by Johannes Schmidt, Vincent Delacroix, and some other people, where you can do more or less intersection theory on the model space of curve, and this strata of differential is implemented. So you can intersect this strata with, I mean, the psi class, the lambda class, and many other classes. So this is how you can compute this intersection number. So you can compute this intersection number for each value of mi, then you do an interpolation, and you get this polynomial. So first remark on this H1 is that there is only a finite number of terms. So this is the terms for g equal to 0 and n is equal to 3. This is a term for g equal to 1 and n equal to 2. And this is for g equal to 2 and n is equal to 0. And this is just a finite number of terms because of some dimensionality constraint in these integrals. Okay, so now let's look. Let's look, for example, at the genus 0 part. So there is this 1/3 factorial which was already there. So that means that the intersection number, so this intersection number in that case, it's 1. So let's justify this, because in that example it's kind of trivial. In that case we are in genus 0, so we look at the strata in genus 0, but this strata in genus 0 is of codimension 0, so you only intersect on the model space of curve. So you have lambda 0 also, so it's only an integral of one psi class over some m0 4 or 5, and in that case you get this one. So this is very easy. Okay, and now let's look, for example, at the equation that you get from the genus 0 part. So let's look at du over dt. So this is u h1 bar. And let's look, so there is the first part plus something which depends on epsilon. What is the first part? So this comes from looking only at this part of the Hamiltonian density. So this is the Hamiltonian density, but here there is a bar, so that means I want to extract the coefficient of ix to the power -1. So that means that I impose that m1 plus m2 plus m3 is equal to -1. And this quantity I have is exactly the Hamiltonian I defined before. So what you get here is u1, where u1 is the first derivative with respect to x. And actually that's an exercise once you have this formula to compute the rest. And the rest is so you get the KdV equation, which was my first surprise. Okay. But actually there is more. There is more, because now you can look actually not at the equation but already at the Hamiltonian densities. And okay, we can do the exercise. Let's try to write these Hamiltonian densities in terms of u and derivative of u. So I remind that u of x is sum of qm I m x m. So now what about the derivative, the x derivative of this u? If I take the x derivative dxi, well then, so m belongs to z, I have to multiply by m minus 1, etc., until m minus s plus 1. And this is m minus s. So this quantity is well known. I will denote it by m with a bracket s, and this is called, so I will put this here. This is called a folding factorial. And well, it's also well known that as soon as you have polynomial in the ni's, well, any polynomial, you can write it as a polynomial in terms of volume factorial. So this is what I call a factorial polynomial. So of course, we already know that these intersection numbers are factorial polynomials. But when we look here, we see that in the genus 0 case, we have a volume factorial polynomial of degree 0. And here, this is M1, 2. This is M2, 2. And this is M1, well, that's M1 and 2 actually. M1, 1. M2, 1. So you see that in the genus 1 terms, you get a homogeneous volume factorial of homogeneous degree. And same thing in genus 2 here, what you get here is a volume factorial of degree 2g, so 4. And that's, well, that's really unexpected from these numbers. So that's, well, that's the first surprise. And actually, this is crucial if we want to write this expression in terms of u and derivative of u. Because, so, and the fact that, okay, I will write this. So the first point, these numbers, they are homogeneous factorial polynomial of degree equal to 2g. And this is equivalent to the fact that we can write h1 as a differential polynomial. So a polynomial in u and the derivative of u. If you didn't have this polynomiality, if you didn't have the homogeneity part, what you would get an explicit dependency in x. That means you would have like negative power of x. Okay, so now let me write h1. The genus 0 part gives you u0 cube over 3 factorial. The genus, well, this, I can write this, I don't want to make, okay, so this part gives you, so it's u0, u1 over 12, so this is an epsilon square. And then the last part is u1 over 24. And no, and sorry, this is the last, another part.
U0, U2. The second term is U0,
U2, yeah, thanks. Yeah. And the last part is U4 over 24. And that's the second surprise, that this Hamiltonian density is exactly the Hamiltonian density, the tau symmetric Hamiltonian density described by the double ramification hierarchy. So that makes an expected connection with the double ramification hierarchy. And before stating the result in its full generality, I want to make a reminder of these double ramification hierarchies. Okay.
So this Hamiltonian coincides, as you said, you have the Hamiltonian of KdV,
yeah,
in your Poisson structure. What about the other Hamiltonians?
Do
they also coincide?
Yeah, that's the main theorem. So all the equations are the equation of KdV, and even more, all the Hamiltonians are, I mean, of course, are the Hamiltonian of KdV, but are the Hamiltonian described by the double ramification hierarchy. And this is something that, okay, I will state the result. Okay. So a quick reminder on double ramification hierarchies. So I just need the Hamiltonian densities, HDDR. So it's similar, it's the generating series for G n, so that G plus n is positive. Epsilon, so there is no minus, epsilon 2G n factorial. I directly write the expression in terms of U and derivatives of U. So sum for S1, Sn positive, and so you take this intersection number, drg 0 a1 an, and minus sum of the ai, psi 0 d plus 1 lambda g. This, so yeah, okay, I don't have the time to recall what's the definition of the double ramification cycle, but this is a cycle of codimension G also, but which is very, very different from this one. And so this intersection number, they are also polynomial in the AIs, and what you do is you extract the coefficient A1 S1, AN Sn, and this Si corresponds to the U derivatives. So S1, US1, USn. And that's what Sasha proves, that this Hamiltonian commute also with respect to the standard, the first person bracket of KDV. And now I can give the main theorem of this talk. I write this here. The main theorem is that HD is equal to HD dr for d bigger than minus 1. And okay, so that's, and I want to give, okay, I will erase all of that. Sorry. And equivalently, we can see this equality as an equality of intersection numbers, and this is, I prefer that because we can generalize that. So what we have, let's look at the coefficient of this differential polynomial. So you start with the intersection on the strata of differential, so minus 1 m1 mn, and 2g minus 1 minus sum of the mi. I put this psi class psi 0d and lambda g. So as we said, this, and then I extract not the coefficient of this polynomial, but let's see this polynomial as a factorial polynomial. So m1 s1 mn sn, this is equal to a1 s1 an sn. Intersection on drg 0 a1 an minus sum of the a lambda psi 0 d lambda g. So I have to finish in 3 minutes.
30 minutes.
30 minutes. Very good.
So is this like some integral transform?
In which sense?
Like Fourier Laplace transform or Melling transform?
No. There's nothing where it's that deep in this definition. It's just that these are the coefficients of the Hamiltonian of the double ramification hierarchy. That's here. and for the hierarchy of neuromorphic differential, if you look at the coefficient of the differential polynomial, then these are the coefficients. And I'm just saying that the equality of the differential polynomial is the equality of the coefficient of this differential polynomial. That's what I'm saying. Okay.
So AI and MI are independent, right? Independent. MI and AI variables.
Yeah. For example, the sum of the MI is equal to 2G minus 2, and the sum of the AI is equal to 0. No, sorry, it's already written there, but the sum of this order is equal to 2G minus 2, and the sum of this order is equal to 0. So MI and AI are Okay, so let me give a word on the proof.
So these classes some homologic classes in the model space of curves, right?
Yeah. These two are in the model space of curves, and of course not equal, actually very different.
So the relation between these classes is something.
So this is really unexpected. Yeah. I mean, the relation between this intersection number is really, really unexpected. Yeah, because I mean these two commutative classes, they come. I mean the definition is really different. For example, I mean if you want to define this double ramification cycle on the model space of smooth curve, well, the condition that you have to look is that this twisted line bundle is isomorphic to the trivial one. So the condition that we had here was the condition on the canonical bundle, which should be equal to a twisted trivial bundle, and here it's a condition on the twisted trivial bundle. So this is really different geometrical objects. Yeah. Okay, so let me say a word on the proof. Well, we computed H1, it's here, and then we wrote it as Hamiltonian density, and what we have seen is that this is H1 of dr, and this starts as U0 cube over 3 factorial plus some correction. So this is established. Now, let's look at the genus 0 part of HD for any D. As we said, in genus 0, this cycle is of codimension 0. So, well, the intersection number is just an intersection on M0 n plus 2. And it's really easy to see that, well, in that case, this is equal to the genus 0 part of HD dr, because in that case, HD dr, this is also a cycle of codimension 0, so you have really the same integral. So the first integral is equal to the first integral of the double ramification hierarchy, which is also, these are also the Hamiltonians of KdV. Moreover, the genus 0 part is equal to the genus 0 part. So using the fact that both hierarchies are integrable, you deduce, and this is kind of magical to me, you get directly that HD bar is equal to HD dr bar. So you don't get quite this equality of Hamiltonian density, you get an equality of Hamiltonian, and actually you can refine this argument to have really an equality of Hamiltonian densities. Okay.
Usually only to zero equivalence does not class improbability does not guarantee.
But But
I think you need maybe.
So these are the methods of
H1. You have H1 equal.
Yeah, H1 equal.
Then of course, yes.
Yeah.
That is because of the uniqueness.
Yeah. I mean, but for me, this is always magical.
It's proof in Sasha's paper and also.
Yeah, exactly.
For integrability, it's also in Siqi Liu and Eugene Zhang's paper.
Okay, this is but I use the paper of Sasha. Okay, something I forgot to say. So, yeah. Something I forgot to say on this theorem is that when we intersect, so we know that these intersection numbers are polynomial in the AIs, and when you intersect with lambda g, you restrict the integral on the moduli space of compact type, the moduli space of compact type curves. And in that case, the double ramification cycle is a homogeneous polynomial of degree 2g. So this polynomial is a homogeneous polynomial of degree 2g. So that means that this integral is a homogeneous factorial polynomial of degree 2g. So the homogeneity that we saw before for H1 is actually general. And okay. So consequence of the theorem is that these integral it's a homogeneous factorial polynomial poly of degree 2g. Okay. So now let's try to generalize this result, right? So all this construction was done for the trivial cohomological free theory. What happened if we want to do the same thing for other cohomological free theory? What the conjecture that we have, and now it's about conjectures. Conjecture 1. Well, the theorem holds. So this equality holds for the Hodge cohomological field theory and for 3-spin. And for example, if you try with the 4-spin, it's not working anymore. Okay. And actually, so.
Sorry, so for 4-spin, you know that it's not.
It's not working. Yeah. Well, actually, what I expect is that you see, like these integrals, we show that these are polynomial, right? So if you insert here the Hodge or 3-spin, these are still polynomial. But what I expect is that as soon as you insert the cohomological field theory, you show that this is not a polynomial. I mean, of course, you cannot expect to have such a simple relation. So you need some maybe correction, or maybe it's completely wrong. I don't know. So that's the first conjecture. The second conjecture is what about the quantum version of that, right? So I need okay.
So sorry, for 4-spin, the hierarchy you construct, you still consider you still conjecture is integrable.
So the hierarchy we construct is still integrable, yeah. That follows from the splitting property. But then we don't know what is this hierarchy, because I mean the number we have are not polynomial anymore, so you cannot repack everything in terms of u and derivative of u. That's really annoying somehow. So I mean there's some work, like I don't know what so the point is, like for 4-spin, for example, you don't have a polynomial, but you have a piecewise polynomial. So maybe what you should do is to just take like one part of the polynomial and consider the hierarchy associated to this polynomial. I don't know what to do, but there could be some, I don't know. Okay, but let me say more on what happened in the quantum context. So as I said, in the quantum context, what we want to do is to, well, be in the more general case where this G is replaced by a L, where L is between G and 0. And what we would like to have is to have L also here. But this is not true. What is true is that, I mean, you have this equality only if the sum of the SI are equal to 2G. So the sum, so yeah, the SI are there. So in fact, for general L, this is a polynomial of degree 2G, but it's not homogeneous anymore. You have all the degrees of the polynomial. And the conjecture is that if you select the top degree of this polynomial, this is exactly equal to the top degree of this polynomial. And what about the rest of the degrees of this polynomial? Well, this is equal to 0 if the sum of the SI is different from 2G. Yeah, that also means that well, the quantum Hamiltonian that we have are kind of a slice of the quantum Hamiltonian constructed using the double ramification hierarchy. And okay. Maybe just to finish, I want to give one application, and it will not be long at all. Okay. Yeah. Okay. One application. I want to look at tau function for the case of the trivial commutative free theory in the classical case. So as we saw, the hierarchy that we constructed is the KdV hierarchy. And also the Hamiltonian we have are the tau symmetric Hamiltonian, so we can construct the tau functions. So let's look at, I mean, we know some tau function of KdV, for example, the Witten-Kontsevich tau function. And I remind that, okay, the correlator of Witten-Kontsevich is given by this intersection number. One d1 psi n dn. And so how to construct this correlator from the Hamiltonian that we defined from before. So what I want to simplify my life, and I insert a tau 0, but that does not change anything because using the string equation, I mean this equivalent to we can remove this tau 0. So using the tau structure, this is equal to the following quantity. So you start with hd1 minus 1, you take the Poisson bracket with hd2 bar, then you take n Poisson bracket like that until hdn bar. So this quantity is it's a differential polynomial, and you want to evaluate. So the evaluation here is the evaluation which corresponds to the initial condition of the associated solution, and the solution of Witten-Kontsevich is the one starting at u of x is equal to x. And as we often do, we can also say, okay, x is equal to 0 because the x variable corresponds to the variable tau 0. But this condition is actually equivalent to taking qi is equal to delta I1 and x is equal to 0. So this might not be that explicit from that formula, so let me just, and I will finish on that, write the formula for n equal to 1. So for n equal to 1, what you get is the following thing. So you get mg 2 bar psi of, let's say, d, and this is equal of 1 over 2g factorial hg bar minus 1. And so since you perform this evaluation, you have to put only ones everywhere. So here you have 2g ones, and then the minus 1 at the end, psi d lambda g. And you get this formula just for free. You don't have to prove anything. And as far as I know, this formula was not known. Okay, and I will finish on this.
Let us thank the speaker. Any questions?
And
Yeah, either informal
formula, or like Heinz formula of H, at least for H1 bar in Kopov type is a formula.
Not that I know.
Okay, if there are no questions, let us thank the speaker again. We'll continue in 5 minutes. А это, видишь, он даже не знает, почему
Сейчас можно построить
ну, просто здесь,
а если мы просто будем представлять?
То есть на уровне
Сейчас, то есть вот, по крайней мере, получается, что у нас есть, если мы берем произвольный проводку, можно вот как у них
Can you define EA equals 1 and
то есть здесь в общем случае, то есть верхняя они могут
This was bracket is the bracket I used for this side. Okay? This is the bracket for this side.
And you used one Q,
yeah.
And you have the Q V is equal to A plus B minus 2 right?
Yeah.
No, it's coefficient of perfect.
Yeah. So now if you
can like
if you take this and you take index QI by QI plus 1. Yeah, okay, you get the same.
Minus 1.
Yeah.
So it transforms.
Yeah.
So I can transform the series like such that they are equal.
Yeah.
Also, so I don't So there is a freedom here. So what can change in general? I can change this knowledge class.
So you can add more steps.
Add more stuff. Yeah. And so in this way I'll obtain different and also there's some this degree controls the number of people. So in H1 it starts with 3 grades. And is my intuition correct that if I consider H0 and if I consider H1 presentation should be like a constant.
Which one?
Then H2 will be 4 and so on. And the sum is equal everywhere. So sum of indices is always say minus 1 here.
Yeah, actually, so like what you look here is the G0 part, and this is really easy to compute.
And the complicated ones are the directions.
It's a bad idea. I think they say that this use another program.
But in practice, it's not just
So, which paper?
This is yours.
Something like that, I think is so it's actually you could say that it is a technical paper, but so it is this you see similar H formation, but of B hierarchy. So and what it follows of course our paper. Some of Q function. So fusion functions are related to this the peak, the one that is related to B and group. So here Sasha Rabin, so he's also one of the authors, maybe the leader of that paper in group. So he continued this line, and yes, he did everything for BTP. I mean, actually, he was supervising Yaroslav. So Yaroslav provided the guidance. And maybe there is some other development, but this is the one I know. Yeah, about Jack, I don't know. So that would be very interesting, but I mean, we try, you know, many, like, there are, you know, these attempts you do, but they listen how well make it to the paper, so we try to generalize reference to something that would be relevant to Jack. But no, not really. So on Platonic language it does generalize, on this Ternonic language, at least we need to do. По экспертному совещанию либо с фактом, либо с техом, мышкой и так далее. То есть как бы что чисто документ не читается так, что сразу тебе однозначно. Как бы как бы следов от этого на документе мало.
The last for today is a talk of Raphael Fessler. The title is Ribbon Gluing and the Real Covid Numbers.
Thank you very much for the invitation. So today we will speak about some variation of this number and some topological models that is quite new. So here the plan of the talk. So I don't know how well known are the classical Rabbit numbers, so I will recall it quickly. Then I will introduce several definitions of the real Rabbit number. Okay, so let's start. So classical Rabbit number are a family of numbers which are indexed by a non-negative integer in the partition lambda. And actually there are several definitions with some correspondence between them. So the first one, the simplest one, is an algebraic definition. So you take a string of m transposition. Actually, you count the number of strings of m transposition such that their product belongs to the prescribed conjugacy class C lambda. Lambda is a partition that we define. We have another definition which is algebrogeometric. So it basically is the number of non-isomorphic ramified cover where all the critical values are simple and the profile over the critical value infinity has profile lambda. So this is called usually simple Hurwitz number. So we will be focused here only on simple Hurwitz number and disconnected one. And there is one last definition which is less common, which is a topological one. I will spend some time today explaining in detail this definition, the topological. So it's the decomposition into M non-twisting ribbons and M disks of surface with a boundary. The surface will have S boundary component, and on each boundary component you will have lambda 1, lambda 2, and so on, marked point. I will explain this in more details in a few minutes. So now some properties of the Hurwitz number. So the first thing, classical, that can be done, we can put all these numbers into a generating function. And this generating function satisfies a partial differential equation, which we heard already about. The cut and join. So the cut and join is something quite simple. It just explains what's happening. You have a permutation, you multiply it by transposition, and you see what's happening. Either it will break a cycle into two cycles, either it will glue two cycles together, depending where you have the element of the transposition. So if you have something like this, and you multiply it by a transposition, either in this case it will glue these two cycles, otherwise it will cut these two cycles. It will cut this cycle. So this is what I just explained. So the cut and join operator is something quite common in combinatorics. It has eigenpolynomials, the Schur function. So these functions are indexed by the partitions lambda, and actually the eigenvalues are known. Well, this is quite classical. It can be found in McDonald's book. I think the first, McDonald's book basically. So knowing these facts, this gives us a nice result. We have that the Hurwitz number can be expressed in terms of Schur function. So basically the generating function of Hurwitz number is exactly equal to this thing, where here it was, how do I go back? Okay.
You should like this.
Okay. Yeah, so with this eigenvalue here. Okay, and another thing which is nice, we have that the cut and join is actually, say it simply, in the group of symmetry of the KP hierarchy. So what does it give us? It gives us that the generating function for Hurwitz numbers is a solution to the KP hierarchy. So these are the main facts and definitions that we will look at today, and we will try to expand them in the case of what we call real Harris number. It will become way more clear why it's called real in a few minutes. So here I summed up what I just said. So we have the algebraic definition, a number of non-isomorphic ramified cover. I added a bonus definition here, the geometric one. We have that the Harris number, well, the keyword here is ELSB formula. We have that the Harris number are intersection number in the moduli space of curves. So I won't go into detail for this. The keyword is ELSB formula. It's pretty well known. Then the topological definition, and we have this cut and join, the Schur polynomials, and it is a solution of the KP hierarchy. Okay, so now we will move to a real Hurwitz number, and I will start with the topological definition of Hurwitz number. And for this, we need to introduce quite some material. So the first thing that we will use is called decorated boundary surface. So a decorated boundary surface is a triple of a surface with boundary, marked point, and orientation in the vicinity of the marked point. All these marked points are on the boundary. Then we have some extra condition. We need that we need the following things. Each connected component has a boundary. So for example, a sphere is not allowed. And on the boundary, we will always have at least one marked point. Something like this is not allowed because here we are missing a marked point on this boundary component. Then we can define the equivalence and equivalence class for this in a quite natural way, and we call this DBSN with beautiful letters. Then we introduce one of the main things with this ribbon decomposition, which is ribbon gluing, and here I need to make some drawing, otherwise it's not very clear. Okay, so what do we want to do? We have a surface with boundary, with marked point, and we want to glue a ribbon to it. So what is happening? We look, so you look at your boundary component, you have a point AI, the point AJ, so the marked point in the definition, one of them, two of them, yeah? And now we have a choice somehow. You can add an extra point, which is not a marked point, it's just an extra point to help us drawing. That we will call AI prime. And here we have also some local orientation near AI. So what do we see? We see that the segment AI prime follows the direction of the local orientation. So we will say that the first sign is plus, and we will have AI here. AJ, so AJ is here. We have a local orientation this way, and we can point an extra point AJ prime here. Here we see that the segment AJ prime does not following the orientation, so we will say it's a minus and AJ here, so G for gluing. Now we want to actually use a ribbon. So what do? We join AA with AJ prime. We can erase this thing. And we join AJ with AA prime, and we can erase this thing, and we erase this part of the boundary. So the boundary is now changed. We have this thing here, this thing here, this one thing here. This is not a boundary anymore. And we keep the orientation that was present at AI before the gluing. So it goes this way, it goes this way. Naively, well, this ribbon is twisted. You see, you took the ribbon and you twisted the thing. Yeah? An example of non-twisted ribbon is something that you start this way, you take your 2 mark point, AI, AJ, you have some orientation, you go after, oh. This is a non-twisted ribbon, and this will be denoted G, AI, AJ with plus plus. Is this construction clear so far, or it's a bit confusing? So far it's just basically just gluing ribbons to the surface using the mark point that we have. Okay, so the main thing, when we glue ribbons, we keep, if you had a decorative boundary surface, you keep a decorative boundary surface. The boundary still has some mark point, you don't break anything, it stays as it is. It will change a bit how it looks like, but it stays a decorative boundary surface. Here, basically, what do we say? So you saw that here, AJ plus plus. So basically, for each time you glue, you need to choose if you have a plus or a minus, or 2 pluses, 2 minuses, and so on. If the signs are different, we call it twisted. If the signs are the same, it can be plus plus or minus minus, it's not twisted. So there is another drawing here that I hope is more clear. So once again, we look locally at the point AI and AJ. You choose a point AI prime and AJ prime if it follows the orientation. If the segment AI prime follows the orientation, you get a plus for here. And if the point AJ, if the segment AJ prime follows also the orientation, you have a plus. On the other hand, here you see that indeed AI prime follows the orientation, but here AJ prime did not follow the orientation of AJ. Yeah, so that's why you get a minus here. These signs here are related. The first sign is related to AI, the second one is related to AJ. Always. Okay. Now what do we do? So we have that decorative boundary surface with all the conditions that we said can always be written this way. So you start with a disconnected union of disks, where each disk has exactly 1 mark point. So you have a disk with 1, disk with 2, and up to n. And then to this you glue ribbon and ribbon and ribbon and so on. You can twist them, not twist them, and so on. Yeah? This is what we call ribbon decomposition of n. So after you glue all the ribbons, you will get some surface, and this surface is obtained by this ribbon gluing, and this is what we call the ribbon decomposition. Okay. Okay, now gluing a ribbon, you also get an extra structure which is important. So when you glue a ribbon, so here it's AI, AJ. Suppose we glue it in a way that it's not twisted, just to ease the drawing. Each ribbon that you glue, you always draw the diagonal, the segment, the diagonal which joins AI to AJ. Yeah, you do this for each ribbon, and we get what we call just the diagonal graph. So basically, all you do, you just for each ribbon that you glue, you also draw the diagonal of this ribbon, and you number this ribbon depending on if it's the first one, second, third one, and so on and so on. What does it mean? That means that at each marked point, say AI, we will have a number of diagonals coming to it. Yeah? It can be 1, 2. depends how many times the ribbon reached it. So this we will denote it, so let's say this way we denote it by L1, L2, here it will be, that we will use LP, and LK. So this diagonal graph have some interesting properties, which we say here. So first, it's an embedded graph. What do we mean by this? We mean that all the diagonal intersects only at the vertices. That means on the point on the boundary, and nowhere else. We have an anti-unimodality, which means that this L1 is a number. It's, for example, ribbon number 8. Then you will have ribbon, I don't know, number 6, and so on. So up to LP, this will be decreasing. And from LP till LK, this will be increasing. Okay? So at each ribbon, at each vertex mark point, you will have this property. So we have what we call the twisting rule. We will call any vertex from L1 to LP, it will be a positive one, and a negative one. And any vertex from LP to LK is a positive one. And we can remark that LP is somehow both positive and negative. And finally, this surface is a homotopy retract. The graph, the diagonal graph, is a homotopy retract of the surface. Okay, so these are the property, and now we can define, at least in terms of topological definition of the Lewis number, is basically just the number of decomposition of surface into ribbon and disk, into M ribbon and disk. And what we want is the following. So if we have a partition lambda, we have lambda 1, lambda 2, lambda S, a partition lambda. So on one boundary component, you will have lambda 1 marked point. On another boundary component, you will have lambda 2 marked point, and so on until lambda S marked point. Yeah? Okay. Okay. Now I will introduce some tools which will be used a little bit later, because for classical Horowitz number, it's quite easy to, for example, make a correspondence between the definition in terms of transposition and the definition in terms of ramified cover. You just use monodromy or Riemann existence theorem. You go from one to the other. If you are looking in some surface which are not orientable, or in our case, it's not that easy. So now what I'm going to do, I'm going to introduce some tools to be able to make a one-to-one correspondence between the topological definition at first and the algebraic definition that I will introduce in 5 minutes. But first of all, we need to introduce all these things, otherwise it won't be possible. Oops. Basically we call, because so far our surface, because of the twisting ribbon, it was possible that the surface was not oriented at all, or not orientable. Now we are in the case where the surface is oriented, and well, that just means that all the local orientation are consistent with global orientation. And now, because everything is oriented, so you have a point A1, A2, AN, and so on, A1 to and so on. All is oriented. So you can read along the boundary component of this mark point. This gives you a cycle. This gives you the boundary permutation. In a few minutes, we will see that it's quite useful. So the boundary permutation is just what in an oriented decorative Brownian surface. What's happening when you read the points on the boundary following the orientation? Okay. So I already talked a bit about the diagonal graph. In the case where the surface is oriented, we have some extra property in addition to the previous one. So the anti-unimodality becomes actually monotonicity. That means that you now hold this thing. Now this one is the number of this diagonal is smaller than the number of this diagonal, and so on and so on. So this is the first property. Second property, you have a face monotonicity. So you look. So each face of the surface has exactly one external edge, so that means here it's already out of the surface. And if you count in this direction these edges, which are the ribbon diagonal, goes in an increasing order. Yeah, another thing which is very different, each edge separates faces, two different faces. If it's non-orientable, it can just not separate two different faces. And we have a last one, which was exactly the boundary permutation, which is as follows. So we have that the boundary permutation is actually just the product of the transposition. So what I mean by this, so let's suppose that everything is oriented, so you will have G of IM GM, so we want everything plus, G of I1 G1 plus En. The boundary permutation, as it was here, is just the product of IM GM, I1 G1, and that's all. So it's actually quite, in the oriented case, it's quite convenient. You just read the ribbon and you get automatically the how the mark points are distributed on the boundary component. Okay, so now I will introduce some more tools. So here is really the tool that we will use for the correspondence. So here we can, in a classical way, just extend the definition of orientation cover for DBS. So basically, we have the usual constraint, and in addition, we ask the following thing. So if you have a non-oriented surface and you take its orientation cover, if this is the point AI, the marked point obviously needs two preimages, one which will denote BI and the other which will be denoted tau of I, where tau is this fixed point free involution. So instead of using this complicated notation, let's write that one will be BI plus n. How to choose if it's BI or BI plus n? You just look at the orientation. If it coincides with downstairs, it's BI, otherwise it's BI plus n. Okay, so now the theorem is as follows. The notation are quite heavy and not very especially understandable, so we'll make an example to hopefully make it clear. What does the theorem say? The theorem says if you have any DBS, you can always construct its orientation cover the decorative boundary surface orientation cover, and there is an algorithm which is quite simple. So let me just give you a concrete example. So let's suppose we have downstairs this decorative boundary surface, yeah? What the theorem says? The theorem says that we take the first thing here and we look at the signs. So we have that the sign plus here is related to 1. So we will write 1. Then we have that here minus is related to 3. So that means we have 6. Then we write its tau related transposition, to say so. And this will be 4, 3. Okay? Then we have 2, 3 with 2 pluses. So here it's simple, it's just 2, 3 on the left, 5, 6 on the right. And then we have the last one, which is 1, 2, 4, 5. And here it will become plus, plus everywhere. And we take the end here. So basically, the orientation cover of this DBS is exactly this one using this algorithm. So here there is a concrete example, which is actually exactly this one. So you have downstairs a Mobius band, and you construct this orientation cover exactly this way. So the circle number is which ribbon, the number of the ribbon. So the first ribbon is 1, 3, and it's 1, 3 plus minus. So it should give somewhere, it should give the third and fourth. So yeah, the third one is 3, 4 as we said, and 1, 6. Yeah, as it should be. Okay. Okay. So basically, the main thing to remember. So we are done with the topological part. The thing to remember is that to a decorative boundary surface, no matter how many twisted ribbon, non-twisted ribbon it is, you can always associate the oriented cover, which is unique. And this oriented cover is basically can be understood as just a product of transposition because of the boundary permutations that I explained somewhere here. Yeah? Is it clear so far or not? Really? Yeah? Okay. Now we go to the algebraic part, which is a bit simpler to understand, I believe. So we will look at the following object. So you take the transposition tau, which is written here, and you look at all the elements which almost commute with it. You want to get the inverse of it. Yeah? So you want tau sigma tau to be equal to sigma minus 1. We can actually describe all the elements that satisfy this condition. They are decomposed into two possible things. Either the cycles come in pair. So let me write an example. So either the cycles come in pair, where we have the following thing. So if I take 1, 2, 3, the tau symmetric cycle, tau related, should be 6, 5, 4. Because if you conjugate 3 by tau, which is here 1, 4, 3, 5, 2, 5, 3, 6, this is tau. If you conjugate 1 by tau, it gives you 4, 2 by tau, it gives you 5, 3 by tau, it gives you 6. So it's, you take the cycle, conjugate it, and inverse it. This is what we call a tau symmetric. And then we have some other thing which is called tau self-symmetric, but actually we will focus only on the first type of cycle, the tau symmetric. Okay. So basically what do we call B lambda? These are the elements which are tau symmetric. So this thing, for example, would belong to what we call B tilde 3. Another example, if I take 1, 2, 5, 4, 3, 6, this belongs to B tilde 2, 1. Okay? Well, we have now that these B lambdas are actually Bn conjugated classes in S2n where Bn is understood as the group of reflection Bn. So you can embed the group of reflection Bn into S2n, and B lambda tilde is just Bn conjugated in S2n. Okay. Now we arrive to the actual definition in terms of combinatorics for the real Hurwitz number. So the definition is actually here. So take a string of transposition sigma 1 sigma m, and you are counting the number of transpositions such that their product times tau sigma m tau. So basically what we are looking at. So these are the number of string of transposition sigma 1 sigma m such that their product sigma 1 sigma m tau sigma m sigma 1 tau belongs to this kind of conjugacy class B tilde lambda. Okay, and we also ask that so if you have IS GS, you ask that GS is always different from tau of IS. Okay, now, so I spent some time with this orientation cover for the following reason. Because when you take a DBS like this, you associate its orientation cover, you have the boundary permutation. This boundary permutation is actually exactly this thing here. Yeah? So basically you have a one-to-one correspondence between the definition in terms of topological definition and the combinatorical one in terms of transposition with tau. Okay, now I will continue a little bit in the combinatoric side. And we will look at the cut and join for these guys. So here I just recall the formal way to define the cut and join. So you take a kind of a center here of this Bn tilde, and well, this Bn tilde are indexed. Well, you can index by the partition lambda, and you can send any conjugacy class C lambda to some variable P lambda, where it's P lambda 1 and so on, P lambda S. Then actually here the cut and join, what we will look at. So in the classical way, the classical case, the cut and join, we look what's happening. So you have some cycles, a permutation, and you multiply it by your transposition, and you are wondering, okay, what's happening? And I explain, either it cuts a cycle, either it glues to cycle. Here it's a bit different. You take sigma, and you multiply it on the left by ij, on the right by I plus n g plus n. So it's actually a quite different thing. Here you really look what's happening when you add on the left and right some elements. And we have that the generating function for the twisted Hurwitz number, as we define, for example, in terms of combinatorics, satisfies the cut and join. This cut and join. So here it should have a sum. Satisfies this thing here. So remark that so far we don't have any explicit explicit formula for the cut and join. So all is done by basic combinatorics, and we got this thing. As a corollary, which is clear, we get that the generating function for real Hurwitz number satisfies this equation, and that's the first result. Now, actually, we would be way more interested by an explicit formula for this cut and join, and this is what we do here. So explicitly, so basically, how do we get this explicitly? You take cycles and you look what's happening when you multiply on the left by ij, on the right by tau I tau j. It will break some cycles, make some new cycles, and so on and so on, and at the end of the day, you get this formula here. So this formula here is actually something interesting, because it's a sum of the classical cut and join that we already saw a bit earlier, with some parameter, some parametric extra parameter r, which is here. But actually this thing is quite interesting, because this operator belongs to what is called the Laplace-Beltrami operator. So it's a parametric family which depends on lambda, which is written this way, so with R, which was a bit defined earlier, and our usual cut and join. Now this operator is actually very well known. It has two things that are well known. It has Jack polynomials as eigenvectors, and we also know the eigenvalues. So a quick remark: if you put alpha equals 1 here, you get back to the Schur polynomials, as we saw at the very beginning. And if you put alpha equals 2, we get exactly to what we had here. What we had here. Okay. Okay. So wait, let's go back. So yeah. So basically, we basically what do we get? We get that our cut and join will be expressed in terms of zonal polynomials. Zonal polynomials are just some polynomials in the family, in the Jack polynomials family, for precise parameter alpha equals 2. Okay, so now there is a classical theorem, well, it's in McDonald's book, which says that the product of Jack polynomials divided by some coefficients, well, the legs and arms of Young diagram is actually equal to exponential of pkqk divided by k with alpha, which is our parameter. And after some manipulation, so we get that exponential of p1 is exactly equal to this thing on the left with Jack polynomials and the denominator. We already had this equality here. We can put alpha equals 2, and we get the following result, that actually our generating function for twisted Hurwitz number can be expressed in terms of zonal polynomials. So if you remember at the very beginning, the classical Hurwitz number expressed in terms of Schur polynomials. And here we get that everything is expressed in terms of zonal polynomials. So here I wrote the first few terms, just to see what it looks like. Okay. And now we can get to the last definition, of Hurwitz, real Hurwitz number, which where the word real will make sense now. So all these things are the following. You look at maps. So you go from a possibly non-orientable surface N. You go to the disk. You have an oriented cover and HUD. You go to CP1. So this we call it F. Here we call it F hat. What else do we? Yeah, we need the. So here is orientation reversing. Orientation reversing. Here is conjugation. And what we are looking at are the following maps. We want them to follow these two criteria. And actually what this criterion means. The first one just means that F is a real map. So what is a real map? A real map is a map from a surface of genus G. So we go to the map of genus G to the sphere. And what we call real here, we have that all the critical values are on RP1. Yeah? And we also have the following thing. So if here you have CP1, you have a critical value here. You ask that in N hat, you have two critical points that are related by the what I call beautiful T here, the orientation reversing map. Yeah? So these points are not really simple in the classical sense, but in terms of real, in terms of real maps, this is we consider it as simple points. So what do we get? In addition, we get that anything is doubled because of these conditions, and the map is of degree 2n. So if it's f hat, the degree is 2n. Yeah, and well, so each critical point comes in pair. Yeah, each critical point of f comes in pair, a and the T of A. Okay.
But is it possible that
sorry?
Is it possible that critical point is fixed by this?
No, we don't want. We don't want any fixed point.
It's an additional requirement.
Yeah, it's no fixed point. No fixed point. Yeah. Okay. So here basically we explain. So because well. Here you can look at two different maps. You can either look at F here, either at F hat. So at this moment we looked at F and we decided we defined all the story of labeling and so on F. But well, obviously you can do it on F hat and it goes together. Then we define all the equivalence class. And you get the following theorem. That actually the Harris number in terms of combinatorics is exactly equal to the number of real maps as defined here, and it's exactly equal to the number of decorated boundary surface. Now the interesting thing is the following. The proof that we have the first proof which uses only generating functions, because actually this story of these things, this idea of looking at map from N to D comes from Chapuis and Dolenga. They got some generating function as well as some differential equation, and it appears that their generating function and ours satisfies exactly the same partial differential equation with the same initial condition, so it's the same thing. The the problem with this kind of proof is you don't understand the correspondence. You can just say it's the same. We won't understand. We have another proof, but it's not direct like in the classical case. The other proof uses 3 different correspondence, one after the other, to be able to explain what's happening. To be able to explain. For example, in the classical case, you take transposition, you can directly get ramified cover. You use Riemann existence theorem, it's direct. Here, in this case, it's not possible for the reason that if you start to look at loops here, for example, something like this, what you will get is a product of transposition, and you don't know what is what, basically, because it's double. So you cannot explain which one is ij, which one is I plus n, j plus n. So we need to use many tools to be able to overcome this little problem. And yeah, that's it. How much time do I have? More? 15 minutes. 15 minutes? Okay, I can. Okay, so this was the part. Okay, I will make a few more remarks on the thing. You know? So, yeah. Okay, so we showed these things.
Did this Chapuis Dalega know cut and join?
Sorry?
Did Chapuis Dalega know cut and join and relation with zonal polynomials?
Yes, they know it. Actually, they made something. They looked in a different context, but they got the same result. Actually, even a bit more general than what we got. They got for Jack polynomials in general. So it's actually one of the remarks. So if we compare to classical Harris number, we have the first 2 definitions, but we don't have any definition in terms of ELSB formula or anything like this, and it's quite a complicated problem. We don't know. Topological definition we have, differential equation we understand, expression in terms of zonal polynomial we understand. The big question is what about integrable system? We don't know anything, I don't know anything, or we don't know everything about integrable system for zonal polynomials. That's a big question. Another question, so here we get zonal polynomials, it's, how to say? It's a very precise case when alpha equals 2. We understand what's happening when the parameter is equal to 1 in short polynomials, but what's happening for general alpha? Is there any understanding what's happening for general alpha? Okay, so this is almost done. Now I just want to make a few remarks, not entirely related to this, but still might be interesting. So in terms of combinatorics, what we looked at were the permutation such that tau sigma tau is equal to sigma minus 1. Yeah? This is what we call Bn tilde. One can ask what's happening with tau sigma tau is equal to sigma. Well, actually, this is known now. It gives us all the theory for Harris number for the reflection group Bn, and once you have Bn, you can go to Dn. And here it's quite interesting. Because, well, the definition, the algebraic definition is very close. Algebra geometric definition is just, well, you also have this idea of involution that switched point, but it's holomorphic. Here it's anti-holomorphic, and then we have holomorphic. And we get that it's actually a solution for the KP hierarchy. But so basically, you will get a generating function in 2 variables, P and Q, and you will get a solution for the KP hierarchy independently in P and independently in Q for the reflection group Bn, which is quite interesting. And one last remark. So Bn, the reflection group, can be embedded into S2n and something known, it's Sn Z2 to the power of n. A question that can be asked, what would be Sn with Zn here to the power of n? And these are actually complex reflection groups. So far nothing is known. So these are some extra questions. Some extra questions. Well, that's it. Okay. What I wanted to say.
Any questions? So, do you know if your numbers are polynomial in the course of the ramification lambda? Or do you expect?
If you have some polynomiality.
Yeah.
I think it was shown via tropical geometry actually that it's polynomial. I think so.
So there is an inequality formula which is known?
You should look at the work of Matlig, and I don't remember the second one.
Okay.
But yeah, they looked at it and not a long time ago, and they find some polynomiality formula.
Geometric definition is an open question.
Yeah, because the classical Hurwitz number, you can define it in terms of intersection theory with the ELSE formula. Here we don't know. This is what I mean by geometric definition. We don't have any moduli space or anything close to it to understand what's going on there. Maybe it's some, well, the idea would maybe to look at some, the real moduli space of real curve. I don't know much to say, to be honest.
Okay, if there are no questions, then let us thank we finish today.
I just take out the.
No. Okay, let us do it in the right way. How to close it? This one? Ошибку что ли? Okay, I think you can.
Okay.
Yeah, it's fine.
Maybe, yes.
Нет, просто надо точно знать. Problem is I don't know anything about the keeping. The continuum equation is just an equation on the PDE, removing a PDE, which is classical PDE, which can be written by something like something like with respect to the t there is some nonlinear term which is written in terms of the Hilbert transform. So this so this is operator, which you can apply here, and which is like this power, which is like this polynomial in terms of your
Anything else? If you try to write down, so here like all of these indices are 0 to infinity, and if you write down it in terms of the variable phi over x, which is just the Fourier transform of this variable, so it's like for the positive and it's like the Fourier transform, and also it's a separator, so it acts like multiplication, and for the negative it acts like then in terms of these phi operators, it will look something like this. It will look like the Hamiltonian for this Benjamin equation, which is some coefficient of Hamilton lambda on angle, and here you have derivative with respect to x and the Hilbert transform, which is just some simple transform. And here is the normal ordering, which means that you should put all the derivatives to the right and the e to the left. So this is just what I know, and this is the quantum version of this classical PD. So if you took this Hamiltonian and if we will decide that all of these are just the functions, not the operators, and write down canonical Poisson bracket for this. I don't know if it means something, but if you just constant, if you just by definition put it like the derivative of the delta function for this field phi, then with this operator and with this Poisson bracket, you will recover this Benjamin equation. Probably it is also related to some hierarchy, I don't know. And I know that as you say, the eigenfunctions of these operators are Jack polynomials, Jack functions. So this is.
So yeah, it should be related somehow.
Yeah.
Okay,
and this Benjamin equation is, in classical cases, like very well understood.
Okay.
In quantum case,
Thank you very much.
You should have the social card for that persons is free. Should not pay. But though if you have that you still have to
do you know the KDB equation?
I think now it's slightly changed, and now it's free for each person, but only with possible branches.
No, I don't know. Yeah, it's I just want to say that the KDB was observed as the equation that describes the waves of the power model. There is a very deep water. This is what, this is how it
Thank you.
Tomorrow, I think the picture is every day.
I will check the website.
Что это выглядит? Ну, это сразу что? Она слабая? Нет? Она не слабая.
Вот это, конечно, я понимаю.
Раздача бесплатной еды. Ничего себе. Ну, конечно, небольших количеств. Что-то есть.
Можно предлагать ему ответить.
Иначе она
Да есть
пропадет.
что-то. Я как ребенок беспочвен за любую бесплатную еду, я раз слышал.
Индюшка, индейка, куриные рулеты, как колбаска с сыром.
Вот это хорошо.
Индейка,
А с чем она?
внутри куриного, вяленая.
Алин. Да.
Только мы.
Передайте.
Удача.
Ну реально, удача.
Ладно, давайте.
Если бы пришли чуть-чуть пораньше, еще бы были пирожки.
Ну, спасибо большое.
Это лучше. Давайте, освободите аудиторию.
Ты пробовала? А что у вас тут было?
Здесь была конференция.
Это мы вам, наверное, мешали.
Нет, мы мешали, звонили на 4-м этаже, меня попросили.
Где у кого была конференция, мы несколько часов назад мешали чуть-чуть.
Чуть-чуть.
Так, остался последний кусочек индюшки. Давайте.
Нет, не хочу.
Через не хочу.
Только уже мусорка переполнена.
Там есть.
Да мы сейчас там выкинем.
Так, я на вас надеюсь, что еды не останется.
Хорошая цель.
А тут еще и удобно.
Я так смотрю, я мама говорила.
Ой.
Не, ну можно с собой выжить, да?
Да. Вот это лайфхак.
Да.
Получается, утро.
Это как-то так, когда я вообще кто-то сказал, что, ребята, ну,
Да? Блин, пиздец. Я тогда очень разозлилась.
я заметил, вы просто агрессия, я такой, да за что, я только пришел. Вы просто херню сделали. Когда? А вы агрессию. Я не то, что тыком, конечно, а просто тогда.
Почему в той игре ты перестал топить за то, что ты
Еще раз, я был уверен в том, что получится.
Нет, это понятно.
Потом попалась Евгения, решила просто выражение.
Ну хорошо, вы меня проверите, я вы будете уверены во мне. Но у нас будет операция по одному и тому. Я сразу скажу, Ярик, это риск, да, но, пожалуйста, доверьте мне и сделайте все нормально, потому что у нас было больше опций.
Типа, это единственное, что меня смутило. Ну, что ты перестал.
Потому что когда я, например, чист, я хочу, чтобы меня риски топили просто.